Hi, welcome to our first hands-on tutorial. In this tutorial, we're going to cover AutoML with tabular data, which is arguably the most common data type encountered in machine learning today. In this tutorial, we're going to show you how easily you can use AutoGluon for classification and regression problems with data stored in tables, where the goal is to predict one column of values based on the values measured in the other columns. Before we begin, please follow the setup instructions and make sure everything's properly installed. You can actually run this tutorial and all the other tabular data tutorials on your own Mac laptop because they're not that computationally intensive. We're going to just give a quick overview of what AutoGluon can do and how you can access its basic functionality. Here we're going to give the example of a data set of diabetes patients from a hospital where they recorded various medical features and information about each patient. The link to the original data set is here. First, we're going to import AutoGluon and specify that our task of interest is what's called tabular prediction. AutoGluon offers a number of built-in tasks that basically allow you to train models for specific data types with just one line of code. Throughout these tutorials, we're going to specify a small subsample of the data only because we want to make sure these tutorials run really quickly for you to just try out. If you want to actually see what kind of performance you would realistically obtain, please set this to a much larger value or just don't subsample the data at all. Now let's load the data. Here we specify that the data lives at this path, which actually in this case is a cloud storage bucket in S3. However, this could just be a local CSV file on your own computer. For example, here's what the CSV file actually looks like. Here we have, various columns, various rows representing patients, and we see that the CSV data is pretty messy, containing strings, numbers, missing values, etc. It's not really suited for most machine learning models. That said, we can load the data via this command, which produces this trained data object that is essentially just a pandas data frame with maybe some additional functionality. We can call head on this object to just keep the first 600 patients data only. And then we'll show just the first 5 rows of the data frame. So this is the data from the first 5 patients. There's 47 columns in this data frame. The original data frame had 60,000 rows, but again, we're only going to be working with 600 of these rows in this tutorial to make sure it runs quickly. And you can see the data contain various features measured in these patients, like their age, weight, what kind of medications they were given, as well as whether or not they were readmitted to the hospital after this visit. So again, each row in the table corresponds to one data point, in this case one patient, where we want to produce predictions in the future for new data points or new patients. Each column is one variable or feature. And so what's really important is that these rows remain statistically independent. That is, you can't have data that, say, is time-based, where values in future times depend on values in previous times. That's called time series data and will not be considered in this tutorial. We're just focused on standard supervised learnings, particularly classification and regression. Here, our goal will be to use these features to predict whether each patient will be readmitted to the hospital or not within 30 days, after 30 days, or not at all. And this, as I said before, is recorded in the readmitted column. Here we can look at some statistics of the readmitted column. We can see in our data set of 600 values, there's 300 values that are no, 300 values that are above 30, and 51 values that are less than 30, meaning the patients were readmitted to the hospital within 30 days after this stay, which is obviously a suboptimal outcome. Now we can apply AutoGluon to this multi-class classification problem. In this case, the multi-class problem actually has 3 possible classes. Here's how we do it. First, we're going to specify a folder where we want to store our trained models. Next, we call task.fit, and we point it to the training data, as well as which column contains the target values that we actually want to predict. This is all we have to do, and AutoGluon will start training models. Here we can see that it's starting training. It found there's 3 unique label values in the target column. It infers the prediction problem is a multi-class classification problem because there's these 3 unique values only. It tells you can optionally change this via certain arguments. It pre-processes the data, and then it decides that the evaluation metric of interest should be accuracy because you didn't specify anything. And then it'll start fitting models. So it'll fit some random forest models, some k-nearest neighbors, some neural network, etc. And then it completes training here. Now we can load a separate data of some new patients. This is typically referred to as the test data in machine learning. It's imperative that you don't load the test data ahead of time to make sure you're not cheating. It's the only unbiased way to evaluate AutoML systems is to only load the test data at the point where you're going to use them to produce predictions and they've already been trained and you're just trying to get a score on how well they do on future data. Again, we can point AutoGluon to an S3 file that's just a CSV file. This could again just be on your local machine, and it will load what is again just essentially a pandas data frame object. Here we subsample the data just to make sure everything runs quicker. We extract the target column values here, that's yTest, and then we drop the target column from the test data just to prove we're not cheating. And here we'll show again just the top few patients' data in the test data set. And here you see they have all the same features as in the training data, but there's no target column information. Now let's use AutoGluon's train classifier to make predictions on the new patients and evaluate how well it was actually able to predict whether or not each patient needed to be readmitted to the hospital after their stay. Here we first reload the predictor object from the output directory that was previously specified during task.fit. This is actually unnecessary here because we're still in the same Python session, but it just shows you how you would do this if you wanted to produce predictions in a new Python session. Maybe you're deploying your models on some separate server. Next, we call predictor.predict on the unlabeled test data frame to actually obtain predictions that we store in ypred. And finally, we evaluate these predictions against the ground truth target values stored in yTest. And here we specify that some auxiliary metrics should be computed as well. And so the evaluation looks like this. The primary metric of interest is accuracy, which AutoGluon just chose by default for multi-class classification. And in this case, it's 52% accurate on our 3-class classification problem. And then it also computed a bunch of auxiliary metrics, including the balanced accuracy, the Matthews coefficient, as well as some per class metrics like the precision and recall for each class, as well as how many test data points belong to that class. And so here you can see AutoGluon struggles to predict the under 30 class because there's just much less data from that class in general. Its precision and recall are much worse than for the other classes. Again, this is just a tiny data set, so you should really run AutoGluon with a larger subsample size to get meaningful performance numbers. Finally, we can print all 600 predictions themselves, and you can see that these really just look exactly like values you would find inside the target column of the training data. Now let's switch gears slightly and go to a regression problem, where the goal is to predict numerical values rather than discrete classes. Here we'll consider predicting the time in hospital variable based on the other features values. This variable measures how long each patient ended up staying in the hospital in days. Here we show a histogram of the distribution of values in this column. And again, we just call task.fit to produce a predictor. We don't need to specify regression or anything like that. Here we just provide the training data, a new output directory where we want to store this new predictor. We specify which is the new target column. And another thing that's different here is we specify time limits for AutoGluon. We tell it should only run for 30 seconds, and within 30 seconds be able to be ready to produce predictions. Finally, we evaluate the resulting trained predictor on the test data. Here we show a shorthand method, evaluate, that takes in labeled test data in this case and internally we'll call predict and score. Now let's look at the output logs from this run. So again, AutoGlon first looks at the label values in the target column, and it shows the first 10 of these values look like this. And AutoGlon then decides that the prediction problem should be regression because this is a floating point. These are floating point values, and there's many unique values observed in this target column. It tells you can specify, you can override this guess, which you probably should if you already know what kind of prediction problem you have. Next, it pre-processes the data and decides that it's going to evaluate performance using the default metric for regression, which in AutoGlon is root mean squared error. Then it splits the data into training and validation sets, and will start training various models on the training set and reporting some internal metrics on the validation sets. Finally, so it'll train, models like k-nearest neighbors, light GBM, boosted trees, neural networks, etc. And finally, it'll create a weighted ensemble that combines the predictions from all these models. And here it actually completed training in just 23 seconds, which is less than our 30-second time limit because this data set, again, is just really tiny, only 600 data points. And here, finally, it prints out the resulting performance of the default evaluation metric on the test data, which is root mean squared error, and in this case, it's 2.5. Note that some of these internal metrics printed by AutoGlon are actually negative because internally AutoGlon is always assuming higher metrics values equals better performance. So it flips metrics that are actually losses like root mean squared error to be negative internally. Now let's go back to the original predictor for our 3-class multi-class classification problem for predicting the readmitted variable and see what actually happened during fit. So this was a 3-class problem, and the default metric AutoGlon chose was accuracy. Again, it'll just automatically guess this or infer this if you don't know or if you don't specify what the metric or the type of prediction problem should be. AutoGlon also infers the type of each feature in addition to the type of prediction problem, basically whether it's a numeric column, is it a categorical column of discrete values, and it'll also automatically handle things like data processing, dealing with missing values, and normalization of numerical values if needed. So here we can look at our trained predictor and see what it, see a summary of what it inferred. So here it guessed the problem type was multi-class once again, and then it guessed the following feature types for each column in the data frame. So categorical features are those that are discrete, assign those like gender and age. Recall age here is actually string intervals of lower bound to upper bound of the patient's age for privacy reasons. Things like the diagnosis, the primary diagnosis, secondary diagnosis, whether or not they were given particular medications, etc. These are all discrete features. The time in hospital variable is a floating point feature in this case. That's actually the target value. And then, or it's not the target value here because we're predicting readmission, remember. So here in this case, this is actually being used as a predictive feature. And then the integer columns include like the number of lab procedures the patient received during their stay in the hospital, the number of medications they were given, the number of diagnoses they got, as well as the number of previous outpatient visits they had. And so internally in FIT, AutoGlon automatically chooses a random training validation split of the data if you don't specify anything. The validation data will be separated from the training data and used to score each model and possibly some hyperparameter settings in the model. Then AutoGlon trains a bunch of models in sequence, and finally it ensembles their predictions all together, trying to see if the ensemble can actually outperform any of the individual models. Beyond making predictions, the predictor object returned by FIT can be used to summarize what actually happened during the fitting process. Here we can call the fit summary method on this predictor, which will print out a bunch of information. For example, what models were trained during the fitting process, as well as how well each model scored on the validation data. The number of models that we trained, the types of models, what hyperparameters were previously fed into fit by you, as well as some graphical summaries of this information. Here's one of the summaries. This plot, you can mouse over each point, which represents one of the models that was trained, for example, the random forest classifier here, and it'll show you the hyperparameters that that model used, how long it was trained for. On the y-axis, what was its performance on the validation data. On the x-axis, what was its latency on the validation data, meaning how long did it take to produce predictions. So you can see for the cat boost model, for a light GBM model here, for our random forest model here, using the Gini split criterion. And here we see the weighted ensemble model, which combines a bunch of these individual models actually had the best performance on the validation data, which maybe is not surprising. And so let's now evaluate all our models again using the test data, but this time let's evaluate each individual trained model that was produced during fit. And we can do this using the leaderboard function, where here we pass in the labeled test data once again, and the resulting data frame returned by the leaderboard function looks like this. It contains test accuracy of each individual model here. It contains validation accuracies of each individual model. It contains the time it took to produce predictions with this model on the test data, the time it took to produce predictions on the validation data, how long it took to train this individual model, etc. Note that the performance of many models decreased on the test data. For example, the weighted ensemble model here had a very high validation score relatively and a much lower test score. Likewise, the light GBM classifier had a much higher validation accuracy than test accuracy. This is because even though the validation data was held out during the optimization of individual models, certain training decisions are still made based on the validation set, and this leads to slight overfitting. This includes decisions like when to early stop iteratively trained models, like the neural network or gradient boosted trees, as well as how to combine the model's predictions into a single ensemble. The more decisions that we make based on the validation data, the less reliable performance estimates obtained from this data become, particularly if we do extensive hyperparameter tuning. This is why it's really crucial to only present the test data after training is totally complete to obtain an unbiased estimate of the true predictive performance of your system on new data. Also, AutoGluon can be used to predict class probabilities instead of class labels. So here we can call predict proba on the predictor, and the resulting object will look something like this. It'll be a vector of length 3 for each patient, where each entry of the vector basically corresponds to the predicted probability of that particular class according to the AutoGluon's best model. Here, this is useful if you want to gauge, say, the confidence in your predictions. Maybe you want to rank or prioritize patients. For example, maybe you want to look more closely at patients who are predicted to need hospital readmission shortly after this stay. Maybe something went wrong during the previous stay. Or maybe we want to just use a different probability threshold to convert our predicted probabilities into classes. Maybe false positives have a big penalty in some particular application, and therefore you want to use a more conservative threshold when deciding how to convert predicted probabilities into predicted classes. Whenever we call fit, AutoGluon automatically predicts with the model that previously displayed the best validation performance on the validation data. This is almost always the weighted ensemble because AutoGluon constructs this ensemble to combine individual models' predictions in a way that maximizes validation performance. We can instead specify to predict with a particular model like this. Here we're specifying that we should produce predictions for the first 20 rows of the test data using the neural network model only. The kinds of data AutoGluon can handle include files of CSV format where each column is separated by, say, commas or tabs, and the rows are on different lines of the file, as well as column-oriented files stored in Parquet format. These are commonly encountered if you pull data from a database. Also, you can use AutoGluon to data that's already been loaded in Python as a pandas data frame. If you have data from multiple tables, it's important that you first join them into a single table where the rows correspond to statistically independent observations, i.e. data points where the goal will be to produce one prediction for one data point on future data. The columns should correspond to individual features, aka things that are measured in your data, also referred to as variables or covariates. For more information about AutoGluon, please check out the documentation. Here we show the documentation for fit. If you go to the following link, which contains all the information you need to run AutoGluon in your own applications, there's lots of extra arguments you can specify to highly customize the system. In addition, if you want to see more technical information about the AutoGluon system for tabular data, check out this paper, which contains all the technical details as well as extensive benchmarks of AutoGluon's tabular prediction module against other AutoML systems across data from Kaggle and OpenML. Our next tutorial will cover data processing in AutoML. AutoGluon's one-line fit behind the scenes implements a complete AutoML pipeline that takes in raw data and outputs accurate predictions. This involves steps like splitting the data into, say, training and validation folds, preprocessing the data so that ML models can actually operate upon it, training individual models, optionally tuning their hyperparameters, optionally ensembling their predictions together, and optionally engineering extra features or selecting a subset of features to feed into our predictors. So what is data processing? Most ML models are just designed to operate on numerical vectors, often only numbers in certain ranges as well. So typically we'll need to transform raw data into this sort of format for the models to actually learn from. Here we're going to assume that you're mostly familiar with standard data preprocessing techniques, and we're going to focus on some subtle issues that may arise and are critical to building a robust, performant AutoML system. If you're not that familiar with basic data processing techniques, please check out these resources. For example, the first of these links covers, it's a Medium article that provides a nice overview of all the most popular data processing techniques that you might find in a standard textbook and you've probably encountered in your own ML projects. The second link here is a Coursera course that from some very competitive Kaggle winners that show just how crucial data processing is to producing the best possible predictions. So first we're going to talk about the data splitting process. Recall that we typically will split our provided data set into a training subset and a validation subset. The predictive performance on the validation data will crucially guide a lot of automated decisions about which model or combinations of models is best, how many training iterations to use for iteratively optimized models like neural networks, what hyperparameter values are best for certain models, etc. It's thus really critical to use a representative validation set that facilitates accurate estimation of generalization performance. However, we don't want to hold out too much training data for validation, since then less data is available for actually fitting our model's parameters. Once the validation set reaches a certain size such that we can accurately estimate predictive performance on new data, additional validation set increases will only marginally improve our estimates. While the size of the validation data reset. Once the validation set reaches a certain size such that we can accurately estimate predictive performance on new data, additional validation set increases will only marginally improve these estimates. While the size of the validation data determines the variance of our performance estimates, how biased these estimates are is determined by the number of modeling decisions we base on the validation performance that we see. By default, AutoGluon will select the fraction of data to hold out for validation as follows. Between 5,000 and 25,000 examples, we hold out 10% of the data, as we want to grow the validation set to a stable 2,500 examples. That is sort of a baseline level that allows us to reasonably estimate held out performance. For larger samples, we only hold out around 1% of the data, which suffices to accurately estimate validation performance if the data set is really large, while allowing us to train on most of the data. If hyperparameter tuning is performed, then we actually double the size of the validation set to mitigate the bias introduced by choosing many hyperparameter values adaptively based on the same validation data. Note that for smaller data sets, it's probably desirable to utilize multiple training validation splits, i.e. k-fold cross-validation, which we'll discuss in a future tutorial. When we do the split, we typically employ class stratification for classification problems. Here we match the proportions of each class between the training and validation data, which prevents a shift in this class label distribution that might otherwise simply arise due to random chance. Here, extremely rare classes remain an issue, and AutoGLON will by default just discard all data from classes that occur under 10 times in the data set. This can be actually adjusted via a user-specified argument label count threshold. AutoGLON trained models thus never predict these discarded classes because the models could anyway only learn very little about them. But we make sure to remember to take them into account when evaluating predictive performance on the validation data. Whether or not a random training validation split is appropriate for a particular application is hard for an AutoML system to determine by itself. It often requires domain knowledge. If you believe that your future test data will actually come from a different distribution than the training data, you should aim to provide the validation set you believe is most representative of the test distribution. For example, data are often collected at different times where some of the predictive relationships might vary over time, and the goal often is to predict on data that will be received at future times. Here, a reasonable strategy might be to reserve your most recent data as the validation set and use the data prior to that as your training set. This will mimic the time difference from the training data that will be encountered during inference. With AutoGLON, we can specify a manual validation set via the tuning data argument like this. Here, we are first performing the steps we just walked through in the previous tutorial, loading the data, loading our manually chosen validations data set. In this case, it's just coming from a different file which contains additional patients' data. And then we are fitting our predictor here, specifying what data to use for validation. Here again, we just use a 30-second time limit, and again, we're doing everything in these tutorials on just a tiny subsample of the data, so we really encourage you to try things out with larger subsamples to really see what realistic performance should look like. So here we can fit the model now with our custom validation set, and again, here's what the training data looks like, here's what the validation data looks like. It looks the same as the training data, it's just the same features measured in new patients. Here we see the fit process. We can see that here that there was 600 rows also specified for validation data. Again, we're just subsampling all the data here, so the validation data just happens to be the same size as the training data, which you would not have in practice. And then AutoGLON just trains its models once again. So here, each time it's reporting the validation accuracy of a model, it's now being measured on that provided tuning data. And finally, we can call the leaderboard function again up here. Right here, sorry. And so we see that the performance on this provided tuning data set of each individual model that was trained looks like this. So if we do that, the final predictor returned by AutoGLON will only have been trained on the training data. It will not have ever been trained on the validation data. This seems a little wasteful because if we want to deploy it on test data, we would ideally like this predictor to be trained on as much data as possible. One way to do this is just to simply refit the same models on the entire data set, merging the training and validation data together after we've used the validation data to figure out what's sort of the optimal hyperparameter settings of these models and what's the optimal number of training iterations to train the iteratively optimized models like neural networks. However, if we choose to refit a model to the full data set, there's no way for us to estimate its accuracy anymore since there's no longer any held out examples. Thus, we just have to trust that this model will perform as well as the copy of it that was trained only on the training subset and evaluated on the validation subset. With AutoGluon, we can refit models to the full data set by taking our trained predictor and calling refit full here. This will refit each individual model to the full data set. Next, after doing that, we will load our test data set and then call leaderboard to evaluate both the performance of the original models that were trained on just a training subset of the data, as well as the refit models that are trained on the full data set. Here, the refit models all have the suffix full appended to them. When we look at the leaderboard here, we see that some of these full models tend to be the best performing models on the test data because, again, these models were trained on more data than their counterparts that were not refit to the full data set. However, for these refit models, we do not have any validation score. Once again, we can't report their performance on the validation set because they were actually already trained on this data, and thus any number we would report there would be highly biased. Now we're going to talk about data preprocessing. Preprocessing is really important and one of the most crucial parts of a successful end-to-end AutoML system. You need to be able to preprocess the data such that your ML models will actually even be able to operate on it, and you need to make sure to preprocess it in a way such that the achievable accuracy of these models is not limited by, say, loss of information from your preprocessing stage. AutoGluon divides preprocessing into two stages. One involves model agnostic preprocessing that transforms a global copy of the data set that gets input into every model. We also apply model-specific preprocessing that is only applied to a copy of the data used to train a particular model, because different models might want different kinds of preprocessing steps to be applied for their particular characteristics. For example, neural networks typically require features to be rescaled because they can't operate, say, on huge numerical values, whereas tree models might not care about this at all. In AutoGluon's model agnostic preprocessing stage, we classify each feature as either numeric, categorical, text, or datetime. This is partly done based on the D-type, pandas D-type of each data frame column. Any remaining uncategorized columns just get disregarded from the data. These are typically non-numeric, non-repeating fields, and thus they probably have really little predictive value, something like user IDs. To deal with missing categorical variables, we create an additional unknown category rather than trying to impute them. This strategy is also used by AutoGluon to handle previously unseen categories at test time. Note that often observations are not missing at random, which is implicitly assumed by imputation methods. And thus, we want to preserve the evidence of absence rather than the absence of evidence. We want to provide now a word of caution about one-hot encoding of categorical features. Most ML textbooks or tutorials will tell you that categorical features should be converted to numerical values through one-hot encoding. If you're unfamiliar with what this is, here's a nice tutorial on Kaggle. Basically, if your raw data from a categorical feature is on the left, the one-hot version of this data would look as it does on the right after preprocessing. It's pretty self-explanatory. However, we do not recommend this as a generic model-agnostic preprocessing strategy. You should only apply one-hot encoding when passing data to a model for which this technique is particularly well suited. This is because one-hot encoding comes with the major downside that it explodes the dimensionality of your data, and numerous alternative categorical preprocessing techniques exist. Certain models such as LightGBM or CatBoost provide special handling of categoricals, as does AutoGluon's neural network, which utilizes learned embeddings to represent categorical features. Here's a quick summary of what that means. Basically, we can assign a unique vector to each category. Say we have a categorical feature that's days of the week here. And the entries in each of these vectors will be treated as neural network parameters that are learned simultaneously with the weights of the neural network. We invite you to read the additional links for more information on alternative categorical data processing techniques. If you do choose to utilize one-hot encoding, make sure to consider how your AutoML system will handle categorical features with missing values, a huge number of possible categories, or previously unseen categories that are encountered in future new test examples. One solution might be to just keep only the top most commonly occurring categories and bin all other less common categories as well as previously unseen or missing categories into a single other category. A related trick is the hashing trick, in which one just randomly assigns categories to a small number of bins such that certain bins may have overlap between different categories. AutoGluon also considers special features that are neither numerical or categorical exactly. For example, many data tables contain fields such as text fields or date-time fields. AutoGluon simply transforms date-time fields using a pandas transformation that converts them basically to integers. Much richer strategies exist to handle date-time features, such as the FastAI library shown here, which provides a featureization of dates, for example, into many individual features like the year, the month, the week, the day of the week, whether it's the start or end of the month, etc., can all be represented as separate pieces of information that may help your ML models. However, we find that the simple integer encoding in AutoGluon seems to work pretty well a lot of the time. AutoGluon identifies text features as those columns of mostly unique strings in each row, which on average across the rows contain at least 3 non-adjacent whitespace characters. This allows us to have a vocabulary agnostic method for identifying these text fields. For AutoGluon tabular models that solely operate on numerical and categorical values, say models like trees, text fields are encoded via numerical vectors of n-grams. In addition to n-grams, AutoGluon also generates additional features from text fields, such as the number of white spaces, the average word length, as well as deep learned representations from pre-trained neural networks, which we will describe in a later tutorial. N-gram featureization is a simple vocabulary agnostic featureization strategy of text fields that works like this. For each individual word that occurs somewhere in any of the text fields of a particular column, we assign one unique feature for that word. Similarly, for each adjacent pair of words, if we have bigrams, and if we include trigrams, we might even include each consecutive triplet of words. Then we just go ahead and count how often each individual word occurred in the text field, each bigram occurred in the text field, and each trigram occurred in the text field, depending on what n we're using here. Of course, this will greatly explode the dimensionality of the data once again. So in AutoGluon, we only retain those n-grams with the highest overall occurrence in the data. To demonstrate how AutoGluon handles these text fields, we'll add a dummy text column to our diabetes dataset. Here we just concatenate some random strings of A, B, C characters together with some probabilities to create a text column that looks like this. Then we can call fit on the corresponding training data that includes text here, just as before. Again, AutoGluon will automatically identify that this is a text column using its per feature classification. Here we see that during fit, the preprocessing step identifies that we have one text feature correctly. Next, it will generate n-gram features based on this text feature. In this case, it generates 12 because there's not that many unique n-grams within this feature due to the low diversity with which we generated this text, in quotes. After that, AutoGLON goes ahead and fits all its models just as before. Here we can look at how the resulting predictor categorized all the features. Here we break down the feature types into raw feature types and special feature types. The raw feature types are things that AutoGLON simply uses the pandas D type to infer, whereas special features include, those date, time, or text fields that AutoGLON uses special processing to identify. Here we just see that the only special feature is features created based on the text field, dummy text. That's what we called that column in the original data frame. After model agnostic processing, we can actually print what the data looks like via the predictor.loadDataInternal method. Here's what it looks like to the ML models that AutoGLON trains. We again have the original columns from our diabetes data here, but then for that dummy text field, we've now generated a bunch of n-gram features based on different words that tend to occur in that field. You can see these n-gram features here at the end. A key concern across AutoML is memory usage, as this often ends up being the bottleneck that causes AutoML systems to fail on certain data sets. For example, those with many rows or those with many columns. Machines with sizable RAM are nowadays easily accessible in the cloud. For example, on AWS, for pretty cheap, you can get an instance that has over 380 gigabytes of RAM. And thus, robust AutoML systems ought to be able to run on sizable data sets, even without any fancy chunking or distributed processing of the data. However, things can easily break down without careful consideration of memory. For example, a lot of AutoML systems train many models in parallel, which may lead to forking processes that duplicate datasets in memory if not carefully done. Similarly, whenever we pass the model agnostic preprocessed data to a model, it is common to copy the dataset so that the model-specific preprocessing won't affect the data other models receive. However, if you're not careful, additional copies of the dataset are often generated during this preprocessing or particular preprocessing stages, and this is important to avoid. AutoGLON's n-gram feature generation in particular is a concerning area regarding memory because it often adds thousands of additional columns to the table. Here's how we implement it in AutoGLON to avoid memory issues as much as possible. We use the scikit-learn count vectorizer here, which implements n-gram processing, and we cap the maximum number of n-grams at 10,000. This seems like a lot, right? Adding 10,000 additional columns to a data set could really massively increase its size. Here we use uint8 to actually store these n-gram counts, since the counts are typically very small integers, and this already starts to help us reduce the memory footprint. And when we actually go to apply this count vectorizer to actually compute the n-grams, we first estimate how much memory the n-grams will actually require once computed, and we iteratively reduce the number of n-grams we will actually use from 10,000 downwards until the estimated memory usage falls well below the current available memory. Here's how this is done. Here we have two functions that implement the downscaling of the vectorizer. This is, it decreases the number of n-grams that are considered, and the top function, getNgramFreq, counts the n-gram frequencies. Here we first consider fitting our vectorizer to the text data, just the text column of the data set, and then we measure how much we estimate the resulting memory of the data set would occupy, and then we just iteratively keep decreasing this thing until the fraction of available memory used by the n-grams is predicted to be not that high. In this case, because again there's very few unique words in our dummy text data set, the predicted fraction of available memory used by the n-grams is only around 7%, so this downscaling is not needed. Let's talk about another data processing issue now. One The goal of supervised learning and most of AutoML in general is to produce predictions on future data that's currently unavailable. This means whenever we split the data into training and validation sets, we should actually compute all the statistics, save for rescaling numerical features, on only the training data alone, and then just use those same pre-processing statistics on the validation data. This is important because it will realistically reflect what we will have to do in the future, as we cannot compute those statistics based on future data. So if you were to compute your pre-processing statistics based on the entire training plus validation data, you might get slightly inflated performance numbers on the validation data. However, there's a different setting of supervised learning, which is called transductive learning. Here, instead of being asked for predictions on unknown future data, we only need to provide predictions for a particular test data set that's already available. If you think about, say, Kaggle competitions, they give you the test data ahead of time. It just doesn't have labels, but you know exactly what data you need to predict on. And there are many real applications of machine learning that fit within this paradigm. In this context, it's very safe to actually do all the data processing on the combined training and unlabeled test data. And it's in fact preferable to actually boost the accuracy. For example, this joint pre-processing over both the train and test data can help you if some numerical values extend beyond their range in the training data, or some categorical features take values previously unseen in the training data in the test data. In AutoGluon, you can do this pretty easily just by passing unlabeled test data as the tuning data argument rather than labeled validation data. It will automatically assume the reason you pass this data is for pre-processing, and it will just merge it with the training data when computing statistics used in pre-processing. Here we show an example. Again, we just call task.fit. Here, just passing in unlabeled test data here as our tuning data argument. And AutoGluon will run its fit, and it will do the pre-processing here, merging both the unlabeled test data and the training data together, but then it will just split the training data in order to create a validation set that has labels for evaluating the resulting accuracies of models. Here's some references for you to look at. The top two here talk about feature preprocessing in general and are good surveys for you to learn more. This one talks about the different alternatives to one-hot encoding that you can apply to categorical features. This talks about learned embeddings for categorical features that you can use with neural networks. They're particularly powerful for categorical features that have many possible categories. Finally, we encourage you to again look at the AutoGluon Tabular paper that goes into deep detail about the preprocessing applied inside of AutoGluon. And if you're interested more on this transductive learning setting, you can read the original paper by Vladimir Baknik. For our next tutorial, we're going to discuss how to train models and how to combine their predictions together into an ensemble that is more accurate than any of the individual models. Rather than technical details of how models operate and their particulars, we're going to focus more on how these models fit into an overall ML pipeline. Here we'll assume you have basic familiarity with different model types, like basic models such as decision trees or random forests, but we're not going to require that you really deeply understand these at a technical level. For more details on how these models actually operate, you can check out the attached textbook that has nice, concise summaries of different kinds of models in chapters 8 through 15. Let's consider a motivating example. Here, let's consider the data set on the left shown in panel A, where we have two features, one on the X and one on the Y axis. Each data point is associated with a target variable whose values are indicated by the color intensity of the data point. If we fit a decision tree model to the data, the tree splits might look like they do shown in panel B, with the corresponding learned regression function implemented by this fitted decision tree shown in panel C. If we were to fit 4 different decision tree models, we might obtain 4 different predictors in each training run shown in panel D if we were to introduce randomness. This could be either through subsampling the data used to fit each of these trees, or through, say, random selection of the features used to decide each split in each of the decision trees. If we now were to just simply average the predictions of these 4 trees, we could obtain an ensemble predictor shown in panel E. The predictions of this model look much better for the data in panel A, and this really highlights at a very simple level the power of ensembling. This is actually the strategy employed in the famous random forest model. Let's consider what characteristics a good ensemble should display. Let F1 through F9 denote the functions learned by 9 differently trained predictors, where Fj of x denotes the jth model's prediction for a data point with feature values x. Here, say, we use predicted probabilities for classification problems. We can construct an ensemble predictor F star of x just by averaging the predictions of the individual models as we previously described. Suppose our task is binary classification, and each predictor either outputs 0 or 1. So they're either very confident the data point belongs to the positive or the negative class. Also assume each predictor has error rate 0.3. That is, given a new data point sampled from the underlying data generating distribution, there's a 30% chance this predictor will make the wrong prediction on this data point. If all of our predictors produce identical predictions for all possible data points, i.e. they make highly correlated errors, then the error rate of the ensemble will obviously just be 0.3 as well. There is nothing to be gained by ensembling. However, now suppose our predictors make statistically independent errors. That is, they tend to make different kinds of errors on different data points. Then the ensemble predictor, F star, will only make an error if at least 5 of the predictors are wrong. To calculate the probability that this happens, we can sum up the probability that 5 of the predictors are wrong, 6 of the predictors are wrong, all the way up to the probability that all 9 are wrong. And this turns out to be bounded above by 0.1. So actually, just by having statistically independent errors being made by our predictors, we have drastically reduced the error rate of the overall ensemble. In general, the accuracy of our ensemble will improve the more predictors we combine and the less correlated their errors are. 2 ways to reduce the correlation of these errors and increase the ensemble's overall diversity are: 1, to train completely different types of models that tend to learn totally different types of functions, and 2, to train different models using different subsets of the data which lead them to learn slightly different functions. In practice, our individual predictors will have different error rates because some models will be better than others. In this case, we probably prefer to construct a weighted ensemble rather than just assigning all models equal weight. Here, we take a weighted average of the individual models' predictions where the weights sum to 1 and tend to favor the more accurate predictors. To learn about more ensembling strategies, we recommend you check out these 2 resources. Let's revisit what happens in AutoGluon training by default. Here we'll again reload the same diabetes dataset as before, trying to predict the same readmitted column, and we'll call task.fit mostly with default arguments. The only change from before is here we specify that the evaluation metric should be balanced accuracy, just to show something different, and we also specify the verbosity argument to encourage AutoGluon to print out way more training details. Then we load the test data just as before, and we call leaderboard on this test data to evaluate the performance of each individual model that AutoGluon trained during fit. And so with this higher verbosity level, there's going to be a ton of output. And so we see that AutoGluon again does some data pre-processing, then it begins training models here. First, the random forest classifier. After it trains each model, it'll print out the validation score achieved by that trained model. In this case, now the validation scores will be balanced accuracy as we specified that as our metric of choice. And so it'll train random forest models, some k-nearest neighbors models here. It'll train a light GBM, gradient boosted tree model here. And this model is an iteratively optimized model, meaning it's trained sequentially in multiple boosting rounds. And so AutoGluon now with this high verbosity level will print the output of each of these boosting rounds. Here we can see that actually we're measuring validation performance after each round, so that after training is done, we can go back and load the model which exhibited the best performance after a certain number of rounds. This is called, and we can also use early stopping to see that if the validation performance is no longer reliably improving, we can just early terminate training of this model. And so yes, there's going to be a lot of rounds from these iteratively trained models. Here we can see the neural network classifier. This classifier shows, or this model shows a good example of model-specific preprocessing that we mentioned before. So here, for example, this model will apply a learned embedding layer, as we discussed before, to the categorical features here identified as these features. And it applies, for example, rescaling and skew correction to certain numerical features. And so this neural network, again, is an iteratively trained model. Here first we print its architecture in MXNet. This is what the raw architecture of the neural network looks like for this particular data set. And we see it trained sequentially in multiple epochs, where each epoch corresponds to one full pass over the training data set of stochastic gradient updates. And again, after each individual epoch, we measure the validation performance of the current model and can use early stopping if we notice that the model has not improved in the last, say, 10 or 20 epochs. Likewise, at the very end, we can just reload the model from the best epoch based on its validation performance. And again, we train some more gradient boosting models iteratively. And finally, the very last model AutoGluon trains is this weighted ensemble that learns how to combine the predictions of these individual models in the best way possible. Here we see it chooses the following weights, and it achieves the following validation score after it has chosen its weights. The leaderboard call on the test data shows the individual accuracy on this test data achieved by each model. Within FIT here, AutoGluon trained many different types of models that we won't be able to get into the details of. But some of these types include random forests, one random forest using the Gini criterion to select the splits of each decision tree, and one using the entropy criterion to select the splits of each decision tree. It also trained an extremely randomized trees classifier, which is a cousin of the random forest model. And again, it trained two copies of this model, one with the Gini criterion, one with the entropy criterion. It trained two k-nearest neighbors models, one using uniform weights to combine the labels of all the nearest neighbors into a single prediction, and one using distance-based weights to aggregate the labels of the nearest neighbors into a single prediction. It trained a light GBM gradient boosted tree model, mostly with default hyperparameter settings, and then another custom copy of this model using custom hyperparameters that we found tend to produce good performance on certain data sets. These custom hyperparameters basically favor trees that are bigger and more diverse. And we also train another variant of gradient boosted trees implemented in the CatBoost library. Finally, the last model trained by AutoGluon is a custom neural network model implemented in MXNet. The basic architecture of this model looks like this. So we have categorical features and numerical features here after all the model-specific data preprocessing has completed. For more details about the neural network, please check out the AutoGluon tabular paper here. Let's get into some basic properties of these different model types. So light GBM and CatBoost, and also XGBoost that's not used in AutoGluon, are currently some of the most popular models for tabular data, and they almost always are used by top Kaggle competitors to win the competitions. Light GBM is one of the fastest gradient boosting implementations, whereas CatBoost offers sophisticated handling of categorical features and is more resilient to overfitting through careful regularization. Random forests and extremely randomized trees are nice, robust models that tend to be performant no matter how you set their hyperparameters. and they're quick to train, but they tend to be less accurate than gradient boosted tree models, except on smaller data sets. And they can also produce undesirably large files if their maximum tree depth is uncapped. Neural networks tend to be among the better models for tabular data sets with many rows but few columns, especially if the underlying relationships between the features and labels are complex, but they're usually less accurate than tree ensembles for other data sets and often are slower to train. K-nearest neighbors models are very fast to train but very slow for inference and are typically the least accurate model in AutoGluon. We only include these because there's certain data sets where K-nearest neighbors tend to be much better than other models. These are either geospatial data sets or prediction tasks that you can solve just by memorizing the training data perfectly. One key difference between AutoGluon and traditional AutoML or ML tools is that things in traditional AutoML tools, things like this tree split criterion or how to weight the K-nearest neighbors model, whether to combine its predictions through uniform weighting or distance-based weighting, these would be normally treated as hyperparameters that we should optimize, meaning we should choose one of these options and stick with it. In AutoGluon, instead we just train a model under each option, and at the end we just ensemble these models together. Here we show the decision boundary of fitted models of different types for some toy binary classification tasks. Here we show the raw data on the left, random forest models decision boundaries in the first column, and neural networks decision boundaries for each data set in the second column. Here each data set is one row, so there's 3 different data sets in this example, and a nearest neighbors decision boundary in the third column. We note that here tree models are constrained to axis-aligned splits. So even though they tend to be highly accurate for tabular data sets, because in tabular data sets the features are typically pretty meaningful, they're human-chosen features, unlike say images or text where the features can be totally arbitrary, what happens in one pixel versus another. In tabular data, a human decided what are meaningful variables. But because these tree models are axis-aligned, that means when we ensemble them together, the resulting diversity is not nearly as great as when we ensemble them together with neural networks and K-nearest neighbors models, whose decision boundaries can have arbitrary geometry. This means even if the latter 2 model types are not as accurate as, say, the most accurate tree models, they still provide very valuable diversity to the AutoGluon ensemble. What happened in the previous fit call? So as we've said before, the high-level operations include splitting the data into training and validation sets, training a model of each type on just the training data, with model-specific preprocessing applied to a copy of this data, and subsequently scoring this model on the validation data by producing predictions for each validation data point. Finally, we construct a weighted ensemble that aggregates the predictions of the individual models in a weighted fashion. Let's now take a closer look at this model ensemble. Here we can first load this ensemble by its name, and then we can just use the getInfo function here on this model to show a bunch of random information that AutoGluon has stored about this model. Of particular note here is the information about its model type. Here we see that it's a greedy weighted ensemble model. Greedy here refers to the strategy by which we chose the weights. And we can see actually the weights of the ensemble here, or which models it places high weight on. So here we see that it actually only assigned non-zero weight to 2 models, the light GBM model and an extremely randomized trees model, where it placed much more weight on the light GBM model. All other models had weight 0, which means their predictions are ignored and they basically don't contribute to the final ensemble. To actually find weights used for the ensemble returned in the previous AutoGluon run, we use the ensemble selection method proposed by Rich Caruana and co-authors in the paper linked below. This algorithm just runs simple greedy forward selection to choose the weights of each model in the ensemble. First, it initializes the ensemble so that all models start with 0 weight. Then, at each stage, it considers adding each possible model to the current weighted ensemble, with weight equal to 1 if this model is not already in the current ensemble, otherwise incrementing its weight by 1. Then we evaluate how the ensemble would perform with this model added based on evaluating the evaluation metric on the validation data, in this case, balanced accuracy. Then, in step 2, we only add whichever model actually contributed most to the ensemble performance on the validation data. Then we repeatedly iterate these 2 steps, each time considering adding all possible models to the current ensemble, and then only adding whichever one actually contributed most to ensemble performance. We stop when there's no more models we can add to the current ensemble to boost its validation performance. This algorithm runs extremely efficiently if we've cached all the predictions of individual models on the validation data. Because the weights of the ensemble were adaptively selected based on the validation data, be aware that the resulting validation score of this weighted ensemble tends to be more overfit than the individual model's validation scores. Nonetheless, this crude procedure for selecting the weights is nice because it can be applied with any evaluation metric, regardless if it's differentiable or continuous. It produces sparse weights which reduce the ensemble size typically. It remains more resilient to overfitting than some weighting strategies, such as using continuous optimization to find weights that are globally optimal with respect to validation score, for example, using regression to find such weights. That concludes the first half of this tutorial. We'll go through the second half of this notebook in the next video. In this video, we'll go over the second half of the training models and ensembling notebook. Here we'll cover topics like stack ensembling, bagging, and the pros and cons of ensembling versus hyperparameter optimization. Recall that in our weighted ensemble, we simply combined individuals' models' predictions via a simple weighted linear combination. However, why should this be the optimal method of combining predictions? In stacking, one instead trains another stacker model that takes in the predictions of the individual base models and learns how they should be best combined. This can be achieved by simply training this so-called stacker model on a newly constructed data set where the features are now all of the base model's predictions, say, concatenated together and using predicted class probabilities for classification tasks, and the target values in this data set would remain the same as in the original prediction task. The stacker model can thus rectify shortcomings of the individual base model predictions and exploit interactions between the base model predictions that offer enhanced predictive power. But how do we know what kind of model the stacker should be? Since we don't know, we can just train multiple types of stacker models, just like AutoGluon originally trained multiple types of base models on the original data features. We can once again aggregate these stacker models' predictions via yet another weighted ensemble, or alternatively, we could aggregate them via yet another stacker model. The idea of feeding the predictions output by stacker models as inputs to higher layer additional stacker models is what we call multi-layer stack ensembling. This has been a prominent prediction strategy in very famous competitions like the Netflix prize, for which the winning team won $1 million with multi-layer stacking, and Kaggle's auto product classification challenge. In this multi-layer stacking strategy, one often still will use a simple weighted ensemble at the topmost layer of the stack. The form of multi-layer stacking used in AutoGluon is shown below, here for 2 layers of stacking and n types of individual base models. Here, the input to each model at the base layer is just the original data features, denoted as input below. Each model then produces predictions which we concatenate together into another feature vector. Then we actually concatenate the original data features with the predictions of the base models, and that is the input for each of the stacker models in the first layer. Subsequently, we apply a weighted ensemble to aggregate the predictions of these second layer stacker models, and that's how we get our final output prediction. Stack ensembling is one technique that you can specify to boost accuracy in AutoGluon. However, its efficacy is limited without another technique that we'll introduce here. To see why, first let's understand that during training in FIT, stacker models must only operate on predictions from base models for data points that were held out during the base model's training. If a stacker model were to be trained on a prediction from a base model on a data point that the base model saw during training, the base model could be overfit to that data point's label, for example, memorizing its label, and thus leading the stacker model to believe that this base model is highly accurate. If we use a standard training validation split, that means we can only use the validation data to train our stacker model. This strategy is known as blending, but it obviously does not generalize to the multi-layer setting, where each additional stacker layer would have less and less data to work with. Instead, in AutoGluon, we use bagging to train stackers only on data held out from lower layer models, while still being able to learn higher layer models over the full data set. Bagging, or bootstrap aggregation, was popularized by Leo Breiman, and the idea goes as follows. In k-fold bagging, we randomly partition the data into k chunks that are disjoint, and we train k different copies of a model with a different data chunk held out from each copy. So here we're showing, for example, k equals 5-fold bagging. We have the original full data set here with all the rows shown here. Maybe in the first fold, we use the last 80% of the data as our training set and hold out the first 20%. Then in the second fold, we might use the first 20% plus the last 60% of the data set as our training set, holding the second 20% out as our validation set, and so on. Thus, we see that every single row in the data set lies in the validation set of one of these folds. That means it was held out from the models that were trained in that fold. With stacking specified, AutoGluon will automatically bag all models. Each model will produce out-of-folds predictions on the chunk of data that was emitted during its training. As just shown graphically, every single data point is out of folds for one of the copies in a bagged ensemble. So we always can produce out-of-fold predictions for every single data point from every single type of model. So just to recap, in the case of 5-fold bagging, for every one of the 5 training validation splits shown above, we would train one neural network for each of the splits, one CatBoost model for each of the splits, and so on. So in total, there would be 5 neural networks, 5 CatBoost models, etc. We call these 5 differently trained copies of the same model type a model bag or bagged ensemble. For example, the neural network bagged ensemble would actually contain 5 individual neural network models. At inference time, new data points count as out-of-folds for every model in a k-fold bagged ensemble, because presumably these points haven't been seen during training. For a test data point like this, we simply average the predictions of each model in the bag and feed the resulting output into higher layer stacker models. However, there's a subtle train test mismatch now, as the input features to stacker models are slightly noisier during training than during inference. This is because during training, stacker inputs are predictions from just a single model in the bag, whereas during inference, stacker inputs are predictions averaged across all models in the bag. To mitigate this mismatch, we'd like to do some sort of averaging of predictions during training as well. AutoGluon uses repeated k-fold bagging, in which multiple randomly chosen sets of k-fold data partitions and model bags are maintained. With repeated bagging of multiple k-fold bags, each data point remains out of folds for one model in each k-fold bag, meaning we can average the predictions over the multiple models for which this data point is out of folds, even during training. Thus, we are able to average some predictions during training as well as averaging predictions during inference, which makes this mismatch less severe. Furthermore, just by having more bags in total, we reduce overall variance in the learning process. If you specify that AutoGluon should use multi-layer stacking during fit, its overall training strategy will look like this. Here, N denotes the number of bagging repeats, and L denotes the number of stacking layers, where each repeat of bagging involves splitting the data into K folds and training K bagged copies of models. First, we iterate over stacking layers. Then we iterate over the number of repeated bags. Within each one of these repeats, we just randomly partition the data into K disjoint chunks. Within each partition, we have a training and validation set here, and we train each type of model on the training set. Then we use that type of model to make predictions on the validation set, aka the out-of-folds data for that model. Then, after we've done this over all of the different train val splits in the K-fold bag, we average the out-of-folds prediction across the repeated bags for every type of model. And then we concatenate these averaged predictions together and concatenate them with the original data features, and that becomes the data features that are then fed back into the next stacking layer. Note that in step 6 here, if we don't have enough time to train all the types of models, that's totally fine. We can just train some types of models depending on what the time limit is. If a particular type of model fails for some reason while we're training it, that's fine too. We just skip over that kind of model and we just start training the next model type. To divide a given time budget between the stack layers, we just divide it equally so that each stack layer has equal time for training all of its models. To decide on N in practice, the number of bagging repeats, we typically will just complete one round of K-fold bagging and then see how many repeats of this can we actually complete within the user-specified training budget. Finally, to actually produce predictions or to obtain a validation score during training, the final set of the averaged out-of-folds predictions are combined via a weighted ensemble with weights chosen via the previously discussed ensemble selection method. So to actually maximize predictive accuracy on your tabular datasets, we recommend you run AutoGluon with automated multi-layer stacking like this. The only change here is that we've specified this auto stack argument, and it will automatically choose the right number of stacking layers and number of bagging folds and repeats for your data. Well, the repeats will just be chosen based on however much time you've specified. So let's see what happened during fit, noting that here we called it with an intermediate verbosity value to print out some more information during training. Again, the pre-processing part of the fit looks similar to before. There hasn't been any change with stacking. Now we're still training models as before, starting with the random forest. The difference to note here is that now the name stacker is appended to each model along with which layer of the stack it is part of. The base models that are just trained on the original data features are layer 0 models. And so here we start training these models and so on and so forth. And here we can actually see one of the models for which we start printing intermediate outputs during its training process, the gradient boosting model, the light GBM model in particular. And here we see the difference is we're not just training one light GBM model, we're actually training multiple light GBM models, even at the 0th stack layer, because we're using 10 folds of bagging here. So here's the first training run of a light GBM model. Then we have the second fold of bagging with a different training validation set here. Then the third fold, fourth fold, fifth fold, sixth fold, seventh fold, eighth fold, ninth fold, 10th fold. And then we're done and we save the entire bagged ensemble of all 10 of these light GBM models before moving on to the next model, say cat boost model. And then again, we train 10 bagged copies of this cat boost model and so on and so forth. And here we start training the neural network model, again printing out its architecture before training, and we start training the first epoch. But we noticed that we ran out of time because we didn't actually specify that much training time in the overall budget. And so actually AutoGluon just decides we're going to skip this neural net model because there's not going to be enough time to train it fully, especially with bagging. And it will just stop and go on to the next model if there were a next model. In this case, that was the last model, and so we're done. And in this case, there's no bagging repeats done because there just simply was not enough training time specified in the budget. If you increase the budget significantly, you'll see that it'll complete up to 20 k-fold bagging repeats, and it will be able to train the neural network as part of that. So that's the L0 models, and AutoGluon will try creating an ensemble out of the L0 models and evaluating its performance. Then it moves on to layer 1 stacking. So now we start training the same set of models again, but this time each of these models is operating on the predictions of the L0 models concatenated together with the original data features. So here we start again with a random forest model. Again, it's denoted as a stacker, and here you see it has the suffix L1, indicating it's a stacker model that operates upon the predictions of other models. And so we train that model, we start training extra trees models as before, now as L1 stackers, k nearest neighbors models, just as before as L1 stackers. And so what we do in this L1 stacker layer is we train every single model type just as before on the original data, but now on an augmented data essentially. And we use the same hyperparameter values for each one of these models as we did when they were base models. And skipping ahead, finally we create yet another weighted ensemble that here now tries to aggregate the predictions of layer 1 stacker models. And this is essentially our layer 2 stacker model, this weighted linear combination of the layer 1 model's predictions. And that's presumably going to be the thing that performed best on the validation data and the thing AutoGluon would use to predict on new data with. And so with AutoStack specified, as we just did, AutoGluon automatically will select appropriate values of k, the number of bagging folds within one repeat of bagging, and the number of bagging repeats, which is just based on how much training time was specified, up to 20. Beyond 20, sort of the benefits are very marginal. And L, the number of layers in the stack, which is typically 2. Here we inspect the test accuracy of each bag model at the various stack layers, again using this leaderboard function. So here you see the leaderboards look similarly to as before, just noting that each one of these models here is actually a bagged ensemble. Note that predicting with any L1 model from the second stack ensemble layer requires first computing predictions from all L0 models. Let's take a closer look at an L1 model. Here we load an L1 model, the random forest, from noting that its suffix includes L1, indicating it's a second layer stacker. And we can call the getInfo method, as we've done before, to see some information about this model. Here we notice that this model depends on 10 children models. Those are the actual random forest models, single random forest models, I should say, that comprise the bagged ensemble that this model is comprised of. Also, we can see the base model names. These are the models whose predictions this model relies on as features. So again, a stacker ensemble model object actually contains 10 different individual models within its bag when we're using 10-fold bagging, and possibly more if we're using repeated bagging. Here's what the actual data that gets fed into this model looks like. We can see this by calling the transform features method that will return the copy of the data used to train a particular model. Here we see that the data looks like this. We have the predicted probabilities of each class from each L0 base model. Here from the random forest classifier with Gini splits, here from the random forest classifier with entropy criterion splits, here from the extremely randomized trees classifier, etc., etc. But also these predictions are concatenated with the original features from the diabetes data set here. So what about hyperparameter tuning, you might ask? So actually, if you look at what people do in competitive data science, say in Kaggle, a lot of those data scientists spend more time on model ensembling with stacking and bagging than hyperparameter optimization, especially because they have strict training time constraints. They want to try out lots of different versions of their data rather than spending time tweaking hyperparameters. One issue with hyperparameter optimization is it often expends significant compute evaluating poor hyperparameter configurations that no reasonable data scientist would consider. Another issue is that if hyperparameter optimization is run for too long, it can start overfitting the validation set. This is counterintuitive because you would expect a good AutoML system would just keep getting better and better the longer it's run for. However, if you allow hyperparameter optimization to tweak too many hyperparameters based on validation data, it can really start to over-optimize. In contrast, stacking, bagging, and just model ensembling in general much more reliably keeps improving performance with additional fit time. That said, the accuracy of AutoGluon's tabular prediction module can still often be further improved through hyperparameter tuning, which you can easily specify via the hyperparameter tune argument of fit. Here we show a hyperparameter tuning example that only trains and tunes light GBM models during fit, and with some custom hyperparameter search spaces thrown in for fun. Here we specify some non-default search spaces that AutoGluon should consider in its hyperparameter search. AutoGluon will not only search over these, but will also search over other hyperparameters as it uses a default search space for every model. For example, here we specify that the number of leaves of each tree might be considered as an integer searched between lower and upper bounds of 26 and 66. The learning rate used during gradient boosting might be considered a real valued hyperparameter that lies between 0.01 and 0.5, and it might be searched on a log scale with a particular default value to use first. And the type of boosting used during training might be a categorical hyperparameter with two possible options. And then we just call fit once again in the same way as before, this time specifying hyperparameter tune and passing in hyperparameters. And because the key in hyperparameters here is GBM, AutoGluon will only train a light GBM model and won't train any other models. And so we just run hyperparameter tuning here, and you can see that it will start running and training many models. And finally, we also still apply ensemble selection since it's so cheap to create a weighted ensemble of different light GBM models now under different hyperparameter configurations. After fit completes, we can examine the performance of all the models trained under different hyperparameter configurations during the HPO process. This can be done using the fit summary method applied to our trained predictor. Here we show the performance of each light GBM model from different trials, where a trial corresponds to a training job that produced a particular light GBM model under certain hyperparameter values. We can also see the best performance achieved after a certain number of completed trials, where recall performance here always is with respect to the validation data. Finally, this fit summary method also produces a couple plots we can look at. This plot shows the HPO results from all the different light GBM models under all the different hyperparameter configurations. Here on the x-axis will be shown one particular hyperparameter. In this case, it happens to show the boosting type hyperparameter, which recall there was only two choices for. And on the y-axis, we show the validation performance, and you can mouse over any model here and see what hyperparameters were used to train that corresponding light GBM model. Here you can see it's not really clear that one type of boosting or another is actually noticeably better for this data. We caution here that the displayed performance numbers are internal metrics produced from the light GBM library, which are actually error rates that have their sign flipped because AutoGluon always assumes internally that higher values of these metrics are better. The other plot produced by FitSummary summarizes every type of model produced during fit. In this case, we only trained light GBM models, so it's not too exciting. But here you can see also the performance on the validation data of the weighted ensemble. In this case, you can also see that the weighted ensemble itself has some hyperparameters. For example, max models and max models per type, which indicate it will only consider at most 5 light GBM models in the weighted ensemble, and at most 25 models in total will receive non-zero weights by the weighted ensemble. Finally, we recommend you check out these references to learn more. These cover things like the different model types, different ensembling strategies, such as different stacking approaches and the related literature on why stacking works, the actual practical stacking approaches that have won major prediction contests, and the light GBM and cat boost papers, just to see how the secret sauce of these models led them to become so popular for tabular data sets. The previous tutorials mainly considered training models with AutoML. In this tutorial, we'll consider doing inference in these models, that is, using the trained predictor to make predictions on new data. In this tutorial, we'll study key considerations in inference and deployment of such models, how to produce predictions in less time, and perhaps we might want to understand our trained predictor via feature importance. Finally, we'll conclude with some practical tips for AutoGluon deployment. First, let's produce such a predictor, and here we'll utilize stacking and bagging to boost its accuracy. Again, we're just working with the same diabetes data as before. Here we specify autostack equals true to produce a stack ensemble of bagged models, and then we load the same test data as before, and finally evaluate our predictions. And again, we're working with a small subsample of data throughout this tutorial. We encourage you to work with larger subsets to get a more realistic sense of how things work, but we just want to make sure everything runs quickly for you. And so we go through the whole stacking process that we previously described, and then we finally can evaluate the resulting predictor on the test data, and we obtain these accuracies and other various metrics. The previous metrics corresponded to predictions produced by the model that AutoGluon believes is the most accurate from its held out data. Recall that we can also evaluate the performance of every model that AutoGluon trained by the leaderboard function here applied to the test data. This produces the following results, where we can see that the stacker models and the output of the last weighted ensemble of the topmost stack layer tend to be pretty good on the test data. We can also see here the time taken for producing predictions from each model on the test data, as well as the time for producing predictions on the validation data for each model. Different models vary greatly in their accuracy and time required to compute predictions, or inference latency, we might call this. Low latency inference may be important for ML deployed in real-time settings where we have to make decisions quickly, maybe one data point at a time. Low memory footprint might be important for ML deployed on edge devices where memory constraints are severe. Overall inference costs might be important for ML deployed in cloud settings where we don't want to pay too much money for a model that is of limited commercial value. So we can see that we have various considerations here that may govern which model we actually think is best beyond just the predictive accuracy. Model ensembles tend to typically be the most accurate, but often will fare worse along these other dimensions. Recall that we can use AutoGluon to make predictions with any of the trained models. Here, let's predict on the first 20 data points in the test data using this light GBM model from the first stacker, the base stacker layer. So L0 here refers to a base model, meaning it operates directly on the original data points, the original data features, I should say. This is actually a bagged ensemble of 10 different light GBM models, recall. Here shown here. And so that means that model will actually take 10 times as long as a single light GBM model to produce predictions, and it may require 10 times the memory. Instead, we can collapse this bag of 10 light GBM models into just a single one that's refit to the full data set. Here, the refit model will early stop at the average of the 10 early stopping points previously used in each one of the bagged light GBM models. So each one of those models had a different validation set and a different training set, so they each early stopped at different points that were optimal for their respective validation sets. Here we call refit full on this model specifically, and it will return the original name of the model. This is the bagged ensemble here, and the refit version of this model, which in this case is just a single model now. And yeah, as I said before, this model will just require 10x less memory and 10x, it'll be able to produce predictions 10x faster if the bagged ensemble is not parallelized. Here we show the process of using this refit full single model for prediction on, again, the first 20 data points. And we can print out its information. Here we see that it has no children models because, again, it's just a single model, not a bagged ensemble. While computationally favorable, single individual models will usually have lower accuracy than weighted, stacked, or bagged ensembles. Model distillation offers one way to try and retain the computational benefits of a single model while enjoying some of the accuracy boost that comes from ensembling. The idea is to train the individual model, which we now call the student, to mimic the predictions of the full stack ensemble, which we call the teacher. Rather than fitting the individual model to the training data target values, one can fit this student model to an alternative data set whose target values are predictions from the teacher. In classification tasks, the teacher provides its predicted class probabilities as targets for the student to predict, which may encode richer information about the class similarities or label noise in the data. We can also blend the teacher predictions with the original target values from the training data for further improvement. Distillation in AutoGluon follows the strategy proposed in this paper, which we call augmented distillation and display below. The overall augmented distillation procedure involves 4 steps. First, we fit the stack ensemble model to the original training data, both its features and labels. Next, we use the training data features to somehow generate a synthetic data sets of fake feature values, which we call the augmented data. The augmented data should ideally follow a similar underlying feature distribution as the training data, and they can be either generated, say, via simple feature permutations or perturbations of values in the training data, or via some generative model trained on the training data features that learns to generate new values that follow the same distribution. Next, we use the stack ensemble model to make predictions on the features in the augmented data set. This produces labels for the augmented data, aka target values that our student should learn to mimic. In classification, these will be predicted class probabilities rather than predicted class labels. Finally, we merge this augmented data set of features and labels together with the training data set of features and labels and train the student model on the entire enlarged data set just in the usual fashion. In this second step, where we're generating augmented data, we typically will generate 5 to 10 times as many augmented data points as there are training samples. This way, the student model can better mimic the teacher by being trained to replicate its predictions at a vast number of points in the feature space. In AutoGluon, we can show how to perform augmented distillation using a light GBM student model, say. Here we call predictor.distill on our previously trained stack ensemble predictor. And here we specify GBM in hyperparameters, which means, again, AutoGluon will only train a light GBM model. Here we've increased the verbosity a bit to see some more output. Here we see that it's distilling with 4,000 synthetic data points. This model now begins training to mimic the ensemble predictions over these synthetic data points. And finally, it completes training and produces some validation score. We can use this distilled model for prediction and compare its accuracy with all the models previously trained during FIT. Here we use it for prediction, where the student name was returned by the distillation function previously. And we can also call leaderboard. Now this distilled model will be included in the predictor object. So here, in this case, the distilled model has the suffix distill shown here. This is its accuracy. Here we just use the default hyperparameters that AutoGluon would normally use for its light GBM models, but we could also specify much smaller hyperparameter values if we want to get more lightweight models as students. Now we're going to shift gears slightly and study feature importance. Often, high accuracy on some test data may not be enough for us to really trust that our trained predictor will lead to the right decisions when deployed. We might also want to understand which features the predictor relies on to make accurate predictions. It's not uncommon that a dataset contains spurious correlations due to how it was collected, or it has some sampling bias. For example, radiologists in 2017 discovered one accurate ML classifier based on X-ray images was basing its cancer diagnoses on the spurious presence of a ruler in these tumor images because dermatologists who were concerned about tumors tended to include a ruler in their imaging. One way to quantify how much each feature individually contributes to an already trained predictor's accuracy is via a method called permutation shuffling. Here we randomly permute one column's values corresponding to the measurements of one feature across the rows of the dataset and measure the resulting drop in predictive performance when the predictor is asked to predict on this resulting data. The size of this drop can be considered the feature's importance score, basically how much predictive signal did this feature provide, because once its values are shuffled, all of this predictive signal is basically destroyed. This way of scoring feature importance is often more trustworthy than many alternatives that make a lot of approximations or are based on often unrealistic assumptions. For our trained AutoGluon predictor, we can compute feature importance scores like this. We have the feature importance function. Here we call it on the test data, so we will be measuring the drop in predictive performance on the held out test data when each feature in the test data is permuted across its rows. Here we show the performances that result, and here you can see some of the top features with the most importance include the primary diagnosis. Recall that our task here is to predict hospital readmission within 30 days, over 30 days, or no readmission on record. So here we see that the most important features for predicting this include the primary diagnosis of the patient, the medical specialty to which, what kind of doctor they're referred to in the hospital, the previous number of inpatient visits that this patient had, their secondary diagnosis, the number of procedures they had during this hospital stay, the number of medications they were on during this hospital stay, etc. And so these all seem like pretty reasonable features that you would expect would help you predict whether or not a patient will need to be readmitted in the near future. If reducing inference latency matters to us, this is still a useful method because we can now retrain a much more efficient predictor that only operates on a subset of the most useful features. For example, here, we only keep those features whose importance in the previous result was positive. Other features basically showed either no drop in predictive performance or even possibly a negative drop in predictive performance, meaning the accuracy of the resulting predictor actually improved when they were shuffled, probably just due to random chance. But features that have non-positive feature importance scores presumably are not providing much predictive signal anyway, and so we might as well just get rid of them. So here we get rid of these features, so we only have a small feature subset. We now create a smaller training data set with only the columns in this feature subset shown here. It's much smaller. As you can see, I think our previous full diabetes data set had something like 40-something columns. And then we can train a predictor on just this reduced subset. And then call leaderboard on the resulting predictor. And you can still see some models are able to do pretty well on a test data set now that only has the subset of features as well. But more importantly, the prediction time has gone down a great deal because both the models end up being smaller when they're trained with less features, and just the amount of computation you need to do to process data with less features is significantly reduced. Next, we're just going to talk about how you should actually use AutoGluon for ML deployment if you choose to pursue this in your own applications. Here we're focusing primarily on applications where inference latency or costs matter. For example, these are often settings where you're making predictions one data point at a time. For these types of settings, here's how we recommend you train AutoGluon. We recommend you use the presets argument here that can allow you to describe some qualitative things that matter to you in the resulting predictor. For example, here we specify the good quality, faster inference preset that says we kind of care about getting pretty good accuracy, but we really want to have fast inference. The only refit means that we will refit all our models, all our bagged models, and collapse them into single models. Recall that that can lead to a massive speed up and reduction in memory requirements. Finally, we also specify another preset, optimized for deployment. This deletes any additional files that are not needed in the final predictor. For example, other models AutoGluon might have trained that are no longer being used, and other auxiliary training files that you just no longer need, so that the resulting file that contains the predictor object is as small as possible and you can deploy it on some limited hardware. If you require even lower latency, we recommend you additionally specify the following fit argument. The hyperparameters argument can not only take a dictionary of hyperparameters, but it can also take some qualitative strings that just say, I would like light models or very light models, where the very light models will be extremely small, the light models will be fairly small, at least smaller than the default hyperparameter settings. And additionally, we encourage you try using distill and hyperparameter tuning, where you might specify a search space over just hyperparameter configurations that you know are pretty efficient. Here's how we can deploy the trained predictor now on a new server. We can load the model from the folder that we previously provided to fit. Again, it's unnecessary here because we're still in the same Python session, but this would be needed if you were in a new Python session. Then we call persist trainer. This makes sure all models are loaded into memory so that AutoGluon doesn't need to load anything from disk when it is given a data point to predict on. Here we can see what the resulting predictor looks like via the getInfo function or the info function. And here you can see the models that it contains and that it requires to produce predictions. Now we go ahead and produce predictions on one data point at a time. Obviously, this is not how you should be doing it if you have the full test data set available, but we're just trying to show what it might look like in a real application. Here's just one patient's data, for example, and then we can produce one prediction for such a patient. Finally, we can evaluate the resulting accuracy of these predictions just as before, along with other performance metrics, which are important always to evaluate when you're considering which model to deploy. We encourage you to check out these references if you want to learn more. This concludes the portion of our tutorial focused on tabular data. In the next portions of the tutorial, we'll concentrate on image and text data and more around deep learning models. So now we're going to talk about AutoML for image data. Unlike the case of tabular data, for image data, it's pretty clear what type of model is the best, a convolutional neural network. In this tutorial, we will demonstrate how to train models for classifying images with AutoGluon. AutoGluon can also be used for object detection in a really similar way. Our tutorial will not dive into the technical details of convolutional neural networks and modern computer vision. For background on this, please study the linked textbook, Dive into Deep Learning, particularly chapters 6, 7, and 13, which provides a very comprehensive and accessible introduction. As for tabular data, AutoGluon will help you easily train models for these vision tasks with just a single call to fit. We begin by specifying image classification as our task of interest and importing AutoGluon. Next, we format our image data set. Here we consider an example image classification task comprised of a subset of the SHOP-E-IET dataset. Each image in this data depicts a clothing item, and the label describes which clothing category the item belongs to. The dataset is really small here just to ensure our tutorial can run reasonably fast for you. Typically, image classification tasks can take quite a while. So here's the command to download this data from our cloud storage bucket and unzip it on your local machine. This will unzip the data and print some basic directory information about the data set, as well as plotting some examples of the data shown here. We can see there's 4 classes: baby pants, woman chiffon top, woman casual shoes, and baby shirt, for which there's 200 images from each class in the training data. Here's what the data would look like on your local directory. There's a training folder that contains the training data with subdirectories containing the class names. Within each subdirectory, we have the 200 images corresponding to that class. Baby pants, in this case, is shown as an example. Likewise, we have test data that corresponds to the same subdirectory structure with here only 20 images per class. You could also have an unlabeled test data set that would just contain only the images without this subdirectory structure based on class names. Let's load these image data into AutoGluon. We do this just similarly as to how we did it for the tabular data sets via task.dataset. Here, when we try and print this training data object, we see that it's an AutoGluon object and it has basically nothing in it. Unlike for tabular data, AutoGluon avoids loading the full image dataset into memory because these can grow quite large. We can work with the dataset by initializing it, calling init here. Now we can look at some attributes, say the .classes attribute, which will list the class labels and their order, which is important because when we call predict, the predictions will correspond to indices in this list. We can now train an image classification model via a fit call. Here we just train it for a very little amount of time, just 3 epochs. To ensure this tutorial runs quickly, we only run 2 trials, meaning only 2 different networks are trained. And here we specify that there's 1 GPU available to use in each training run. If you don't have a GPU, you have to set this equal to 0, but it will take very long, probably. Convolutional neural nets are really designed for GPU accelerated hardware. So here's the call to fit. It looks pretty similar to what we had for tabular data. And again, many of these arguments are optional. And here's the output. Let's actually look at the live. Let's actually run this command live to see something more exciting because it will print some dynamic output. So here what we see is that When we called fit, this job scheduler started preparing training of networks on the GPU. Here we see that the scheduler is planning to train 2 different networks because we specified that in this num HPO trials argument here, num trials, sorry. And each of these trials will involve training one network with some particular hyperparameter values, and it will be trained for 3 epochs. Here we see that the first epoch has just completed and the validation accuracy is 0.35. Now the second epoch completed, and so on and so forth. So let's skip ahead and just look at the final output. Looks like this. Within fit, basically the data set is automatically split into a random disjoint training and validation subsets. Multiple networks are trained under different hyperparameter values. Here there's just 2 of them. And finally, the network with the best hyperparameter configuration is selected based on its performance on the validation set. Here below, we plot the validation accuracy achieved by this network. In the final step of fit, this best network is refit to the entire data set, merging both training and validation subsets, using the same hyperparameter values to produce the model that will be used for inference. Here's how you can plot the resulting best validation accuracy achieved by any of the networks for the trained classifier. Given a new image, we want to use our trained classifier to predict its label. Here's how to do that. Here we see that this image is classified as baby shirt with confidence 49%. We can also print the predicted probability of each class assigned by the classifier. We see that the classifier thought another plausible class could be woman Schiff on top, which seems reasonable to me. Now we load a test data set of new images and evaluate our classifier over all images in this data. As I showed before, the test data basically has the same subdirectory structure as the training data, and it's super easy to evaluate the accuracy. We just call classifier.evaluate. It will call predict internally and then calculate the resulting accuracy of the predictions. What happened during fit? Let's print a summary. Again, we can call classifier.fitSummary just like we did in the setting of tabular data. Here we can see that some basic statistics about the model fitting process, such as the number of classes, the best hyperparameter configuration here, the number of resources available for each training trial, etc. Here we can see some information about each training trial corresponding to the training of one network, including the hyperparameter configuration that was used and the resulting accuracy on the validation data, here called the classification reward by the hyperparameter optimizer. As for tabular data, there will be a summary of models plot that we can mouse over and look at some more detailed information about each model saved in this file. And we can also see the best validation performance achieved so far after this many completed training jobs on the x-axis. In this case, we just have 2 training jobs, so it's not a very exciting plot. Let's talk about what actually happened during fit. First, the data was pre-processed and split into training validation sets. Pre-processing includes resizing and cropping images to ensure they're the right size for our models, as well as normalizing the values at each pixel based on their statistics across the data set. We can optionally apply data augmentation to increase the size of the data set available for training. For example, you can tell AutoGluon to use the simple but effective mix-up augmentation strategy by specifying the fit argument shown here. Mix-up is a really simple trick in which you take 2 images and mix them together, as shown here, to create a new synthetic image whose label is basically just the combination of the 2 images' labels. Another step of fit is to load a pre-trained convolutional neural network from GluonCV, which is a repository of pre-trained computer vision models that have been trained on a large data set of images. usually the famous ImageNet data set. By starting from a pre-trained network and fine-tuning this network's parameters on our data set, the network can transfer its previously learned knowledge of useful image features like edges, textures, etc., or parts of objects even, to improve what it learns from our labeled data set. This is particularly important if our data set is pretty small, as is the case here. Transfer learning enables us to achieve good accuracy with less data than we would otherwise need to provide in order to achieve the same accuracy if training the network from scratch. Of course, you can still disable transfer learning just by setting used pre-trained equals false in fit. Here's sort of what the model zoo looks like in AutoGluon. The available models shown here, their inference latency on the x-axis and their accuracy on the pre-training task shown on the y-axis. Next, we need to suitably set up our network architecture for the particular classification task of interest. Here, in this case, it was classifying images into one of 4 classes. That typically means that we need to modify the output layer of the pre-trained network, which will have been pre-trained on some other task. So typically what we'll do is we'll chop off the output layer of the network, randomly create a new output layer, in this case an output layer that outputs 4 values corresponding to the predictive probability of each class. We'll randomly initialize that new output layer, but we'll copy the parameters from all of the lower layers from the network trained on the source data or the pre-trained task. Then we will train the output layer from scratch with randomly initialized parameters while simultaneously updating the parameters of all the other layers on our own data set. We will repeatedly train neural networks under different hyperparameter configurations to find the best hyperparameters to use. Each training run of a network might leverage multiple GPUs, and 2 training runs of networks with different hyperparameters might be run in parallel on different sets of GPUs as well. For example, if your machine has 4 GPUs and you specify num GPUs per trial equals 2 in fit, then AutoGluon will at any given time be running 2 training jobs in parallel, each using 2 GPUs. Hyperparameter tuning will be described in more details in the next tutorial. The next step, after we found the best hyperparameter configuration for our network, is to retrain a network under the same hyperparameter configuration for the same number of epochs that were optimal on the previous validation set, but now on the merged data set that contains both the training and validation data, aka the full data set. We can optionally construct a more accurate model ensemble of multiple networks by specifying the fit argument ensemble. Here we use a very simple ensembling strategy that's popular for deep learning in particular, called deep ensembles, in which you just train multiple copies of the same neural network just with different random initializations. And there's also some additional randomness in the training process due to stochastic gradient descent, which operates on random mini batches of data. Because image classifications are much larger and slower than tabular data models, it may often not be preferable to do ensembling, especially sophisticated ensembling like stacking, which is why we just stick with the simple deep ensemble strategy used here. Since the neural network optimization is highly non-convex, even just retraining copies of the same neural network with the same hyperparameters on the same data suffices to create a diverse ensemble. For more, see the following references. In particular, check out this Medium blog post to see some benchmark results when we applied that one-line fit call to various Kaggle competitions involving image classification. Check out the Dive into Deep Learning textbook for more background on computer vision models and especially convolutional neural networks. Check out the Gluon CV paper for more information about the pre-trained models that are available and how they were produced. And then check out this Bag of Tricks paper, which describes some tricks you can activate inside AutoGluon that might help you boost accuracy in your image classification tasks. In the previous tutorial on using AutoGluon for image data, we saw that deep learning involves tons of design decisions, we call these hyperparameters, that affect the performance of the resulting model. Some common hyperparameters include choices around network architecture, such as how many layers should my network have, how many weights in each fully connected layer, how many filters in each convolutional layer, and of what size. Should we add residual connections, what activation function should we use, etc., etc. Furthermore, around the optimization of the network parameters, there's also many hyperparameters that need to be chosen. For example, which optimization algorithm to use, what learning rate to use for this optimization algorithm, how to set a dynamic learning rate schedule, and so on. Additionally, we might want to regularize our network to avoid overfitting. Here we encounter questions such as, to what degree should we use the following regularizers, including dropout, weight decay, things like batch normalization, and others. Furthermore, we have questions around transfer learning. Should we initialize our network from a pre-trained model, and if so, which one should we be using? Finally, there may also be questions regarding data augmentation, such as, should we augment our training data with synthetically generated examples? And if so, which augmentation technique should we use? There's now, at least 20 or 30 augmentation techniques that have become popular for image data because it's pretty easy to think of reasonable transformations of image data which should not change the underlying label. This tutorial will help you handle these issues. Unlike the models we previously saw for tabular data, for which reasonable default hyperparameters were existing that we could get pretty good performance with, the complex neural networks used for image data and also those for text data are often limited to suboptimal accuracy unless their hyperparameters are appropriately chosen. Because it's usually unclear what hyperparameter choices will be good for a particular dataset, deep learning has sometimes been referred to or cursed as dark magic or alchemy. There's also a joke about grad student descent, which evokes the idea of a deep learning PhD student blindly tweaking things in an effort to make progress. To address this issue, AutoGluon trains many networks automatically with different hyperparameter choices for each. Instead of having to know what specific hyperparameter values to use, you can instead specify a search space of many hyperparameters to consider, and also specify how to search through this hyperparameter space for the best configuration. If these are properly specified, you may be able to achieve superior accuracy within less training time, but even using AutoGluon's default hyperparameter search space and search strategy should allow you to achieve reasonable accuracy if you let fit run long enough with many trials. In this tutorial, we'll work with the same image classification data as before from SHOP EIET. Recall that fit partitions the provided data into training and validation sets automatically. Instead of the defaults, here we'll show how to specify which pre-trained neural network candidates AutoGluon should consider during fit. Given such a list, AutoGluon will try transfer learning from the different networks in this list to identify the best performing candidate. In this example here, we consider two candidate pre-trained networks, ResNet 18 and MobileNet v2. Here we define this as a categorical search space, meaning a search space of discrete options to select from. In this example, the MobileNet has a multiplier parameter, which itself we decide should be a searchable hyperparameter. Also a categorical search space here, containing the options 0.25, 0.5, or 1. In this case, the multiplier parameter controls the width of the MobileNet's layers. Beyond specifying the space of hyperparameter configurations to consider, you can also tell AutoGluon what strategy it should employ to actually search through this space via the AutoGluon searcher object. AutoGluon supports various search strategies to seek out the best hyperparameter values. This process of finding good hyperparameters given a search space from a given search space is commonly referred to as hyperparameter optimization or hyperparameter tuning. After the searcher has specified which hyperparameter configurations to try next, AutoGluon relies on a scheduler to actually launch and orchestrate training jobs under these hyperparameter settings. First in, first out scheduling simply runs training jobs in the order that hyperparameter configurations are suggested by the searcher. If a training job does not require all the available compute resources, the scheduler may launch other jobs in parallel while sufficient compute resources remain available. A straightforward hyperparameter optimization strategy is to simply use this first in, first out scheduler with a random searcher that simply suggests random hyperparameter configurations from the search space. This seems very naive, but random search can be surprisingly competitive in practice and is much better than grid search for optimizing over many hyperparameters simultaneously. Bayesian optimization is a technique that uses previously tried hyperparameter configuration, validation, and resulting validation performance observations to learn something about which hyperparameter configurations might be promising in the future. From a set of previously tried hyperparameter configuration, validation performance pairs, Bayesian optimization fits a probabilistic model to these pairs called the surrogate model to actually estimate the underlying function that maps hyperparameter configurations to the validation performance of a model trained under this hyperparameter configuration. It then uses the probabilistic posterior estimates of the surrogate function to decide which hyperparameter configuration to try in the next training job. Here we follow an acquisition function that controls whether we prefer to try a configuration we're confident should perform well or a configuration whose performance we're highly uncertain about. Note that we really have to do both in order to gradually converge upon the best possible hyperparameter configurations. This is known as the exploration-exploitation trade-off. After a new training job completes under a suggested hyperparameter configuration, we use the resulting performance produced by this hyperparameter configuration to update our surrogate model, and we keep iterating this process. Link above provides a nice interactive tool to get some intuition for Bayesian optimization. So here, suppose we have one hyperparameter on the x-axis, and the y-axis, pretend up here, shows the validation performance of our resulting models trained under this hyperparameter. Here, so pretend the purple function represents the ground truth performance that will be achieved under each hyperparameter configuration, so that 5 would actually be the best possible hyperparameter for configuration that leads to the maximal validation accuracy, say. Here in gray and black, we show the probabilistic surrogate model that we have fit to the data so far. In black, the estimated function. In gray, our uncertainty about this estimated function. Suppose for now we've only so far tried training the hyperparameter configuration shown here, say 0.5 about, and this was the resulting performance we saw. Which hyperparameter configuration should we try next? Bayesian optimization uses this acquisition function shown in green to decide this. The acquisition function should ideally trade off between configurations we're uncertain about and configurations we think are promising. So here in the first step, the acquisition function told us to try the hyperparameter near 1 first. And so we try that value and say it ended up performing this well. Then we use that information to update our surrogate model. And again, we'll now have a new acquisition function corresponding to the new surrogate model, which will tell us which hyperparameter configuration to try next. In this case, say it's this red point. Now that we've tried this hyperparameter configuration and seen that it actually performs worse than the previously tried hyperparameter configuration, the resulting update to our surrogate model suddenly makes us realize that we're very uncertain about the performance for large hyperparameter values since we've only tried small ones. So now the acquisition function tells us to try the largest possible hyperparameter value. So now we go and try that one, and so on and so forth. We keep following the acquisition function, trying the hyperparameters it suggests, and recording their resulting performance and updating our probabilistic surrogate model. And you can see that by following this process, we pretty much converge upon the global optimum here. And there's very little uncertainty left in the function at the good regions of this hyperparameter space. Similarly, we can construct another search space to identify what optimization hyperparameters work best for our task. Here we demonstrate this for the Nesterov accelerated stochastic gradient descent optimizer, specifying a real search space that instruct AutoGluon to search within continuous valued ranges, optionally on a log scale shown here. Note that you can use analogous AutoGluon code to search the hyperparameters, here constructor arguments, of any Python object that gets passed into the training function. Here we show how you can use Bayesian optimization for hyperparameter tuning inside of AutoGluon's fit. In this case, we'll use the AutoGluon skopt searcher, which uses a Bayesian optimization implementation implemented from the scikit optimized Python library. Here, just for fun, we'll perform Bayesian optimization using a random forest surrogate model with acquisitions based on the expected improvement acquisition function. Here we can specify the search strategy as a fit argument. skopt here stands for scikit optimizes Bayesian optimization implementation. And we can specify various search options for this Bayesian optimization, including the base estimator, i.e. the surrogate model as a random forest, and the acquisition function as the expected improvement. Note that in this demo, we're using a really short number of training epochs and a really small number of total HPO trials just to make sure things run quickly. You should really set these to larger values in practice and just to get a better sense of how these things actually work out. So once we've specified these things and we call fit, it'll start launching training jobs under various hyperparameters suggested by the Bayesian optimization. Here, recall again that we had decided our hyperparameters included the choice of pre-trained model. It could be either the ResNet 18 or the MobileNet with certain hyperparameters of its own, as well as the choice of optimizer. Because the optimizer itself has hyperparameters, here the optimizer is an object that we can't print out its hyperparameters in this Python dictionary easily. But here you can see, for example, in the first training job that we will be trying the ResNet 18 as our pre-trained network to fine-tune. Here we also called fit with a verbose flag, so it'll print a lot more output, such as what these actual networks look like. And you can see they're pretty large. Just printing out their architectures takes quite a while. And so, yes, it'll, just as before, it'll specify running different training jobs under different hyperparameter configurations. And then at the very end, it'll run one final fit on the merged training and validation data with the best hyperparameter configuration that it found. Here we can see the performance, the course of training essentially in each individual trial of HPO. Again, we're just running 2 epochs here, so it's hard to discern many trends beyond that things tend to improve in the first 2 epochs. Finally, we can see the best validation accuracy achieved was 0.4 or 40%. We can evaluate the resulting model on our small test data set once again, just as before, and we see that it has an accuracy of 50%. In standard Bayesian optimization, we wait until a training job completes to see what validation performance of the corresponding fully trained network is, and then we decide what hyperparameter values to train next. We can also measure the validation performance, however, of the network after each epoch within a training job, as we just saw in the previous plot. If a network displays poor performance in the first few epochs, this is probably not a promising hyperparameter configuration to explore further, or a network that's worth spending a lot more compute training. Instead, this training job may be preemptively terminated early to free up compute resources to start training a different network with different hyperparameters. This kind of strategy is known as hyperband in the literature, and here's how you can use it in AutoGluon. In the context of image classification specifically, all we have to do is call fit once again and just specify that our search strategy is now hyperband, say, instead of the skopt searcher. And hyperband has its own options you can set. These are optional, so you don't need to set them unless you know what you're doing. We can then run the resulting fit, and after a long time, so here we actually run things for a longer number of epochs to show the benefits of this early stopping strategy, and we show a much larger number of trials to really show you that some trials get stopped early while others are allowed to train fully. And so this will take you a lot longer to run on your machine. But the end result looks something like this. You can see here that some of these trials that tended to perform much worse than other trials were early stopped right away at epoch number 2 already, or epoch number 3 technically, starting at 0, because these trials there was already trials that were performing much better by the time they hit epoch number 2. We can see that the resulting accuracy on the validation data of the best model found during this hyperparameter search is 80%. Hyperband uses random sampling to propose configurations and successive halving to prune them early on in the training process. Successive halving basically just terminates the worst bottom half of the current training jobs every few epochs. However, this may be way too aggressive. Some hyperparameter configurations that are actually good, meaning they would at the end of training display good performance, might just happen to exhibit poor performance at an early or certain training stage. For example, things like dropout or using a small learning rate tend to require more training in order to actually get the same quality of performance. But then if you keep training longer, actually these kinds of networks may get better performance than their counterparts that are not using the same dropout, say. To avoid being guaranteed to kill all these good hyperparameter configurations due to this early termination, we instead run numerous successive halving brackets in hyperband where random networks in every bracket are allowed to train for all epochs. And an increasing number of the networks in each bracket are actually allowed to train for all epochs. So here we show 4 different brackets of hyperband. In the first one, we're pretty aggressive, and we kill many, many of the training jobs early on, but we allow only the ones that even in early stages already displayed good performance to fully train. However, in subsequent brackets, we are less conservative now, and we allow more of these networks to fully train. For example, in the final bracket here, we let all the networks that remain fully train. We can evaluate the model we just produced from our hyperband search on the test data, just as before, and we see that it achieves almost 90% accuracy. As next steps, we recommend you try playing with AutoGluon's various searchers and schedulers to see how they affect the resulting image classification accuracy. Make sure to increase the number of epochs and the number of hyperparameter optimization trials to actually get a realistic picture of the behavior. For large-scale hyperparameter tuning, you can actually use AutoGluon to easily distribute these hyperparameter optimization jobs over multiple machines by clicking on the following link here, which will take you to a tutorial. Here's some references if you're interested in learning more about hyperparameter optimization. Despite its name, AutoGluon is not just for Gluon or MXNet models. We already saw in the Tabular prediction module that AutoGluon had integrated many third-party libraries like LightGBM or CatBoost. Here we demonstrate how AutoGluon's hyperparameter optimization methods can help you tune various pieces of your own non-AutoGluon, non-MXNet models. As an example, we consider a PyTorch model for classifying images from the famous MNIST handwritten digit dataset. To run the second half of this tutorial, you'll need to make sure to have installed PyTorch. We first explain some of the search spaces supported by AutoGluon. These include simple spaces and nested search spaces. Each search space describes the set of possible values for a hyperparameter from which the searcher will try training models with particular values during hyperparameter optimization. AutoGluon also enables search spaces inside user-defined objects using certain decorators, and you can also decorate functions to automatically make them tunable. Basically, all you have to do is add one decorator to your existing code and it becomes tunable by AutoGluon searcher and scheduler. Let's start by importing AutoGluon. Now let's look at what an integer search space might look like. Here we can just specify an upper and lower bound. We can also sample a random value from the space as follows. This might be useful for the random search procedure. Real space is basically a continuous valued interval. We can also specify that the values in this interval should be searched on a log rather than a uniform grid. And then we can also print a random configuration from the search space once again. A categorical search space is one that consists of a discrete set of values from which the searcher should choose one option. The first value listed corresponds to the default setting that will be tried during the first trial of HPO. A categorical space can also be used as a nested search space, where its options themselves may be search spaces. Here we show categorical space A, B, C, where A, B, and C themselves recall were search spaces. When we call A, B, or C.rand and draw a random configuration, we end up with a random one of these search spaces from which we can again sample a configuration. A list space is a type of search space where the searcher will choose one option from each element in the list, where each element would be a search space also in the nested context. And finally, the searcher will construct a list of these choices. This could be useful for something like specifying network architectures, which might require choosing, say, the width of each layer. This is also helpful to avoid having to convert between different data types in your existing code. AutoGluon Searcher will, if your code wants to see a list, AutoGluon Searcher will provide it a list if you just specify that the list search space should be used. In the example below, the first element of this list is an int search space sampled ranging from 0 to 3. The second element is a categorical search space sampled from the choices alpha or beta. We can see a random configuration here corresponds to a integer from this integer search space and a choice from the categorical search space, and these themselves are put together in a list. A dict space is basically the same thing as a list space, just for Python dictionaries instead. In the example below, key 1 here is a categorical space where you have values alpha or beta as the options, and key 2 is an int space. And when we draw a random configuration of this search space, it itself is a dictionary with particular values for these keys. Now we'll talk about how you can insert search spaces into arbitrary Python objects and functions. In particular, you don't really need to modify your existing code much to make it searchable. First, we'll talk about an searchable object. With just adding one AutoGluon Python decorator, any object returned by a user-defined class can have its constructor arguments turned into searchable hyperparameters. In this example, consider the myObject class here. That would be your existing code that takes in, say, some constructor arguments, name, rank, static value. All we have to do to make it searchable is declare it as an AutoGluon object with this decorator. Inside the decorator, we can also specify a default search space should we choose to, shown here. Now when we instantiate myObject, we can print myObject and note that it's not actually a real object. It's just an AutoGluon object that has not yet been instantiated until we actually ask for a particular configuration of this object when we call rand. Now that we sample a random configuration of this object, we do get a Python object, and it has particular values for its constructor. We can also use AutoGluon to tune any training function. Typically, the training function will contain your script for training a model, but it could be used in other contexts as well. Here we assume that this function takes in various keyword arguments, or args, as its hyperparameters. Usually your training script will evaluate the model somewhere, either at the end of training or after every epoch, and log this information. All you have to do to make this tunable by AutoGlon is add an extra reporter object that AutoGlon provides and also log the performance of your training function in the reporter object as well. Here we show a dummy training function that doesn't do too much. This would be the code that you would have to have originally, where the only difference might be the addition of this reporter object, which we've here made optional so that actually your original function could run regardless. The only difference here is that when the reporter is provided, we record both, say, the epoch information and some performance score, in this case just some dummy score that just sums up 3 arguments. And then all we have to do to make this existing function searchable by AutoGlon is add an autoglon.args decorator. Again, we can optionally specify default search spaces for this function if we want to. For the arguments of this function, I should say. Here we show all different kinds that we covered in the early part of the tutorial. Now let's start hyperparameter tuning this custom code. First, we need to create a searcher object. Let's just start with a random searcher. Here we call the searcher on our training function, which recall we had defined the default search space as the combination of all the previous search spaces we previously talked about. When we call searcher.getConfig, the random searcher will return a random configuration from the search space, printed here. For categorical hyperparameters, it will only print the index corresponding to the choice of the discrete options that has been selected. Here's how to run one training job with this hyperparameter configuration specified by the searcher. All we do is we call our training function, again with its args, and we pass in the particular config that we just had from the searcher. And we can see that when we run the training function, recall all the training function did internally was compute some performance as a sum of 3 arguments, and then print out all of its argument values. In this case, you can see all the arguments are actual values, no longer AutoGlon search spaces. Now we can tune the argument values of this training function by creating a scheduler that serially orchestrates 7 training jobs under hyperparameter configurations that will be specified by our existing random searcher. We create this first in, first out sequential scheduler. We pass it the training function that has already been decorated. We pass it the searcher that we want to use. We tell it that it can use 2 CPUs for each trial, and no GPUs in this case. We tell it to run 7 trials here, and we say that the time attribute corresponding, say, to iterative training, maybe epochs or boosting rounds going back to our tabular prediction module, here in this case will be named epoch. Then we call scheduler.run, which will begin launching the training jobs and begin the hyperparameter optimization process. Scheduler.join jobs will aggregate all the results of all the different hyperparameter training jobs. Then we can call scheduler.getBestConfig here, which will print out the best configuration that we've seen so far, as well as getBestReward, which will print out the best achieved performance during the hyperparameter optimization. In this case, we can see there's 7 different hyperparameter configurations that are tried, and we also print out the performance of each one. 1, 2, 3, 4, 5, 6, 7 here. And the best configuration is finally printed at the end, which is shown here, as well as the best performance value. Now that we've demonstrated the basic building blocks that you can use to tune arbitrary pieces of your own code, let's demonstrate their usage in a practical application. Here we'll consider training and hyperparameter tuning a PyTorch neural network on the MNIST image dataset. Oh, that was not supposed to happen. Reset. Now that we've introduced the basic building blocks that can allow you to tune arbitrary pieces of your own code. Let's demonstrate their usage in a practical application. Here we'll consider training and hyperparameter tuning a PyTorch neural network on the MNIST image dataset. Let's first import the necessary packages from PyTorch. Here's some example images from the MNIST dataset from each class 0 through 9. We'll apply some standard image transformations to our training and validation images as follows, and then we'll load the datasets which are already built into PyTorch. The main training script is something that looks like the training code you normally write for fitting networks to the MNIST data. If you want to apply AutoGluon to tune your own models, this is where you would put your own training script. You see we specify the device to run on. We have some argument values that will govern training, like the learning rate, weight decay, number of epochs, etc. We have a training loop that operates in one epoch. We have a testing loop that operates in each epoch. We have the accuracy, etc. And so the key difference here is that we need to add this reporter object from AutoGluon into our training code. And whenever we get a validation score, accuracy in this case, we just report it in the reporter as well as wherever else we were storing it before, and we can report it at each epoch in this context, which will allow us to use preemptive schedulers like Hyperband. Let's talk about how you will use AutoGluon for hyperparameter optimization in this context. First, you will have an existing neural network architecture in PyTorch that we will convert to be searchable by AutoGluon. Next, we'll convert the training function to also be searchable by AutoGluon. And finally, we'll create an AutoGluon scheduler and launch the hyperparameter optimization process. First, we need to convert an existing network to have searchable pieces. This is done again by just adding our AutoGluon.object decorator shown here. So here, this class.net code, all of this code would just be existing PyTorch code. In this case, implementing a 2 convolutional layer with some fully connected layers on top of it, convolutional neural network. That's pretty simple. To make this object searchable, all we have to do once again is just add the ag.obj decorator. And here we add it also optionally defining some default search spaces to consider. Here we consider searching over the hidden conv parameter and the hidden FC parameter. The former defines the number of channels in the convolutional layers of the network, and the latter defines the width of the fully connected layers of the network. Now let's make the training function searchable. Recall the training script we had gone over before. All we do now is we write a wrapper around this training script and add the AutoGluon.args decorator. Here we just use a small value for the number of epochs. That's not really a hyperparameter to search. And we just use a small value to make sure things run quickly for your purposes. But in practice, you would obviously want to set this to a much larger value. And here we specify searching over the learning rate and weight decay arguments as real valued hyperparameters that are searched on a log scale. Finally, we create a scheduler. Again, AutoGluon provides 2 schedulers that you can choose from for HPO, the first in, first out scheduler and the Hyperband scheduler. The latter only makes sense if your training job or your training function operates in something like epochs that has some sort of iterative nature such that early termination even makes sense. Each scheduler relies on a searcher to determine which hyperparameter configurations should be tried. The default searcher, if unspecified, simply draws configurations uniformly at random from the search base. That's what we'll do here just by not specifying the searcher. Inside the scheduler, you should specify the resources to use for each training job. Here, 4 CPUs, 1 GPU. The number of trials to run. These are individual training jobs. What attribute corresponds to time or epochs or iterations. In this case, it's called epoch. And what attribute corresponds to the reward or the performance measure. In this case, it's called accuracy. Specifically, we're going to measure validation accuracy here. And this is what this scheduler looks like now that we've created it. And finally, we're ready to launch the hyperparameter optimization process and see what's the best hyperparameter configuration we can find. So we just call scheduler.run and scheduler.joinJobs to collect all the results. Because we specified num trials equals 2, there's only 2 different hyperparameter configurations the scheduler gets to run in this case, because we want to make sure this tutorial will run quickly for you. We can plot the test accuracy achieved over the course of training because we stored it in the reporter after each epoch. And we can plot this now under each hyperparameter configuration that AutoGluon tried out. Here the different hyperparameter configurations are represented in different colors. And you can see that the better configuration is the orange one, shown down here after the 4th epoch. And the validation accuracy achieved under this configuration was 98.9% accuracy. To conclude this tutorial, we'll introduce one last hyperparameter optimization strategy. When tuning neural networks, we often want to early terminate unpromising trials to free up compute resources, and hyperband scheduling can save a lot of wall clock time. However, hyperband relies entirely on randomly sampled configurations. As it completes more training jobs under different hyperparameter configurations, a good AutoML system would ideally learn what sorts of configurations tend to work well and hone in on these promising regions of the search space. This is exactly what's done in Bayesian optimization. Bob is a recent hyperparameter search strategy that combines the early termination strengths of hyperband with the better than random configuration proposals of Bayesian optimization. See the linked paper for more details about Bob. AutoGluon provides an improved asynchronous Bob implementation that can be used to tune your custom models. See this linked paper for details about how Bob was extended asynchronously. Here we create a scheduler to implement the asynchronous Bob search. This scheduler is simply our standard hyperband scheduler, but now we specify its searcher to be a Bayes-opt searcher. The searcher will more cleverly propose configurations based on past experience, while the hyperband scheduler will still monitor training jobs and early terminate those which do not appear promising. When we run the scheduler, it looks the same as the other schedulers. Here again, we're just running it for a very few number of trials to ensure the tutorial runs quickly for you. And we can print out once again the best configuration that was found. For more information, please see these references.
Hello everyone, I'm Xinjian Shi from AWS. Next, let me introduce how to use AutoGluon to deal with text data. In the first section, I will explain the basic usage of the text prediction task. Given a new natural language processing dataset, you can, from AutoGluon, import text prediction as task, and then call task.fit to get a model. In the second section, I will introduce how you may configure the search space of this text prediction task. Also, I will explore the usage of different hyperparameter optimization algorithms in AutoGluon. In the third section, I will investigate a setting in which you have a combination of text data, categorical data, and numerical data. Okay, so let's first start with the basics. So here in this basic example, I will use 2 NLP datasets. One is the sentiment analysis dataset, and another is the sentence similarity dataset. So first of all, let me import the basic dependencies. For the sentiment analysis dataset, we will use the Stanford Sentiment Tree Bank dataset, which contains pairs of movie reviews and their sentiments. This dataset is a binary classification problem in which the goal is, given a movie review, we need to classify whether it contains positive sentiment or negative sentiment. Okay, so let's first load the data and view some examples. As we can see, this data set is a pandas data frame that has two columns, one sentence column and one label column. For the label column, label equals to 1 means this sentence has positive sentiment, and label equals to 0 means this sentence has negative sentiment. To train your model, we can simply do the following. From AutoGluon, import text prediction as task, and then we can call task.fit, and we specify the train data, we specify the name of the label, which is label in our case. And also in this example, in this tutorial, I've set the time limit to be 1 minute because I'm using a single G4DN12X large instance. If you do not have GPU and only have CPU, you can specify a longer time limit, for example 1 hour or 5 hours, or you can simply set it to be none, which means there's no time limits. Okay, we can see it's training and it has finished the training. So after the training has been finished, we will get the training curves of all the trials. And next, we can use predictor.evaluate to evaluate the model on the dev set. So here we just call predictor.evaluate dev data matrix equals accuracy. And then we can see for our trained model, the final dev accuracy is 82.45% accuracy. Okay, and then we can get the prediction using predictor.predict. So here I have two sentences. The first one is, it's a charming and often affecting journey. And the second sentence is, it's slow, very, very, very slow. To get the sentiment of these two sentences, we use predictor.predict, and we specify the sentence to be the batch of these two sentences. And now let's see the results. So here for the first sentence, it's a charming and often affecting journey. The sentiment is predicted to be positive. And for the second sentence, it's slow, very, very, very slow. The sentiment is predicted to be negative. For classification tasks, apart from using predict, you can also choose to output the probability of each class via predictor.predict proba. Here, we use this predict proba and we specify the sentence to be the batch of these two sentences. And let's see the results. So here we can see for the first sentence, the probability of being positive is very high, it's 0.998. And for the second sentence, the probability of being negative is higher than the probability of being positive. So the probability that this sentence contains negative sentiment is 0.773. Okay, now let's see another data set, the sentence similarity data set. So here the goal of sentence similarity is to evaluate the similarity between two sentences. And in this example, we will use the semantic texture similarity benchmark for illustration. So as we can see, the input are two sentences and the output is similarity score, so it's a regression problem. So let's load the data. So we can see it's still a pandas data frame and it has 3 columns, sentence 1, sentence 2, and the score. So here we can see a plane is taking off and an airplane is taking off, has a score equals to 5, and a man is smoking and a man is skating has a score of 0.5. So here, if the score is higher, it means it has a higher similarity, and the range of the score is 0 to 5, as we can see here. Now let's train a regression model with task.fit. So here, The logic is similar as the previous example. We just train it by specifying the train data, we specifying the label equals to score. Even if it's a regression problem, there is no need to specify that it's a regression problem because internally we will figure that out automatically. And here we can see that this one is training, and also it's similar that we specify the seed and specify the output directory. Okay, so now let's wait for a while for the training to be finished. Alright, it has finished, and we can see that these are the training curves of the 4 trials. Okay, next we can call .evaluate to calculate the metrics on the dev dataset. And here we do the following. Predictor sts.evaluate dev dataset, and we specify the metrics to be, since it's a regression problem, to be the root mean square error, the Pearson's correlation, and the Spearman's correlation. And now we can see the results of this predictor. Okay, we can see the RMSE is 0.78, and the Pearson correlation is 0.85, and the Spearman correlation is 0.85 also. Alright, next we use our train predictor to calculate the similarity score among these sentences. The first one is the child is riding a horse, and the second one is the young boy is riding a horse, and the young man is riding a horse, the young man is riding a bicycle. And we evaluate these similarities, the similarity between the first sentence and the second sentence, and first via the third and first via the fourth. And let's see the results, and we can see that the model thinks the first sentence is most similar to the given the child is riding a horse, which I think is also similar to what human beings will be thinking. Okay, so let me briefly explain the very basic usage of a save a model and load the model. We can directly call predictor.save, and we specify the directory, and then we use task.load to load the predictor from this save directory. And after that, we can still call the predictor sts.new.predict, and we can find that it has the same score as our previous predictor. Alright, so what's happening inside? Internally, we build the network based on pre-trained natural language processing models, including BERT, Albert, and Electra. The general architecture is shown like this, in which we have a pre-trained backbone model, and in fact, in this tutorial, we use the Electra Small in the implementation. And on top of this backbone model, we add some task-specific layers. And all these models, for the backbone models, we initialize them via the pre-trained weights. And for the task-specific layers, we use random initializations. And for a more detailed explanation of pre-trained language model and state-of-the-art fine-tuning, you may refer to the D2L book. In addition, we run multiple trials with different hyperparameters simultaneously, and we will return the best model on the validation dataset. This certain logic is powered by the pre-built hyperparameter optimization algorithms, which will be explained in the next section. Alright, now we have understood the basics about the text prediction task. In this section, we will learn how to customize the search space, and we will try out different HPL algorithms. In this section, we will use the paraphrasing identification task for illustration. The goal of this task is to predict whether one sentence is a restatement of the other. So first of all, let's load the data, and we are using the Microsoft Research Paraphrase Corpus, the MRPC dataset. So here, for the dataset, we can see it's also a pandas data frame, and there are 3 columns: sentence 1, sentence 2, and label. And also, let's show some samples from this dataset. And for the first pair, they are paraphrase, and for the second pair, they are not paraphrase. Okay, so now let's understand how to explore a customized search space with random search in AutoGluon. In this example, our goal is to search for some hyperparameters like warm-up, learning rate, job how, layer-wise decay, number of task-specific layers, and the question is how to do that in AutoGluon. So here, actually in AutoGluon, we use this ag.space to define the search space. So here we specify this hyperparameters variable. We say for the model, we are using this BERT for text prediction basic, and we further define our search space. So here for aggnet.numLayers, we set it to be ag.space.int 0 to 3. This means it will choose it to be from 0 layers to 3 layers. And then similarly, we set the data dropout to be a categorical false true, which means it will choose either false or true for this data dropout. And also for the warm-up portion, we choose it to be a real value between 0.1 to 0.2. And also for the layer-wise learning rate decay, we choose it to be real value between 0.8 to 1.0. For the learning rate, we choose it to be a real value between 1e minus 5 to 1e minus 4. And apart from specifying the search space for the model, we can also specify our hyperparameter optimization algorithm. So here, we specify the HPO params, and we say for the scheduler, we use the first in, first out, the FIFO scheduler, and for the search strategy, we use the random search. Okay, so now we have defined the hyperparameters. Next is call fit to train the model. Similarly, we specify this train data and the name of the label. And one difference here is also we pass these hyperparameters into the fit function. And then after we call task.fit, it will search the best hyperparameters based on random search because we define that in this hyperparameters. So we can see that it is searching, and since we set the number of trials to be 5, it is searching for this number of trials. And now we can see that this is final training curve. Okay, so let's see about the final performance. So here we call predictor.evaluate to get the performance, and we can see the final accuracy is 82.35%. The F1 score is 87.46%. Apart from getting the performance, we can also check what's the best configuration in this random search. We can do that by accessing the predictor MRPC.results, and we choose the best config. And we can see that for this best config, we have the following results. So for the data dropout, the choice is 1, which means it chooses to turn on dropout, and the number of layers equals to 2, and layer 1 decay close to 0.9, and learning rate something, warm up something. So these are the configuration of the final model that we adopted. In addition, let's check some prediction results. So here, for this example, I have selected 3 sentences. So the first sentence is, it is simple to solve NLP problems with AutoGluon. And second sentence is, with AutoGluon, it is easy to solve NLP problems. And for the third sentence is, AutoGluon gives you a very bad user experience for solving NLP problems. And we can see that it's for the first 2 sentences, they should be paraphrases. And for the first sentence and third sentence, they should not be paraphrased. So let's check the model's prediction. So similarly, we use predict and predict proba to get the prediction and the probability. So here for this model, for the first pair, it predicts that they are paraphrases, and the probability is very high, it's 0.998. And for the second pair, it's the first sentence and third sentence. It gives the right prediction, and the probability is 0.59. Okay. Apart from random search, we can actually use Bayesian optimization in AutoGluon. So here, next, I will show how to utilize the skopt as the searcher. Basically, the difference between Bayesian optimization and the random search is that Bayesian optimization will train a surrogate model to approximate the performance of the hyperparameter configurations. Whenever we observe the performance of a new set of hyperparameter, we update our posterior about the surrogate model. And then in the next trial, we will try to see the performance of the configuration that best balances the exploitation and exploration trade-offs. So let's see how to do that in AutoGluon. We just specify the hyperparameters, the hyper-HPL params, to use the search strategy equals to skopt. And then similarly, we call task.fit to train the model. And now we can see that it is training. So let's wait for some time. Okay, now we see that it has finished the training, and this is the final training curve. So similarly, let's get the prediction, and here we also get the accuracy and the F1 score, and we try to get the best configuration. And for this specific searcher, the accuracy is 83%, and the F1 is 88%. And we can see the best config is like this. So for the number of layers it's 1 and error decay equals to 0.83, and also it chooses to use dropout. And similarly, let's see how it behaves in our manually designed samples. And we can see for the first two pairs it also gives true, and the probability is 0.997, and for the second pair it predicts false and probability is 0.82. Alright, so next we can also use the hyperband algorithm. Different from random search and Bayesian optimization, hyperband tackles the HPL algorithm in a different way. So here for random search and Bayesian optimization, these two methods explore the hyperparameter configurations one by one. But in hyperband, it borrows the ideas from multi-arm bandit, and in hyperband it will try to explore multiple configurations simultaneously. And during this exploration process, it will try to early stop the bad performing configurations and only keep training the promising ones. So in this presentation, we will not touch details, and if you are interested, you can check the original hyperband paper. So here, in AutoGluon, you can use the classical hyperband by specifying the scheduler to be the hyperband scheduler. And also here we use the classical version in which it's hyperband plus random search. So here similarly we can call task.fit to train to conduct HPL on the training data using the hyperband algorithm. So here, due to the time limits, so these are pre-calculated results, and we can see that for the hyperband scheduler, it is able to explore more configurations, much more configurations than both in random search and the Bayesian optimization. So here, this is a final training curve. And we have also evaluated the depth score. So here, basically for the hyperband, we can see that it reaches the 88.81 F1 score and 83.58 accuracy, and it also chooses to turn on dropout. It chooses the number of layers equals to 2 and the linear decay equals to 0.91. So this is the choice of the hyperband algorithm. And also, let's try to see how hyperband performs in our manually designed samples. And we can see for the first pair, it predicts their paraphrase with 0.998 probability. And for the second pair, it predicts their null paraphrase with 0.799 probability. Next, let's investigate the setting in which we have multiple data types, including text data, numerical data, and categorical data. Actually, this is very common in real-world applications because usually text data won't appear alone. Text data are usually mixed with other common data types like numerical data and categorical data. Thus, in the text prediction task, we handle this case. So, let's see an example. So here, for this example, we will reuse the semantics textual similarity dataset that we have used. First, we load the dataset, and we can see that there are 4 columns: the sentence 1, sentence 2, genre, and score. We can find that for sentence 1, sentence 2, these two are text columns. For genre, it's a categorical column, and for score, it's a numerical column. So for this data set, it contains all three types of columns that we are interested in. Next, let's try to predict the score with sentence 1 plus sentence 2 plus genre, so that we are predicting a numerical column with 2 text columns plus 1 categorical column. Let's see how to do this with the text prediction task. In fact, it's very straightforward. We can just need to call task.fit, and we specify label equals to score, and it will automatically use the 3 other columns as a feature column to predict the label. And internally, it will pass the content of the general column and figure out that it's a categorical column with categories equal to 3 possibilities: main captions, main forums, and main news. So after calling the fit, we will train the model, and due to the time limit, these are trained already, and this is the final training result. And then we can evaluate the model. We calculate IMSE, Spearman's correlation, Pearson's correlation, and these are the results. In addition, we can also train a model that predicts the genre with the other columns by specifying label equals to genre. In that case, it's 2 text column plus 1 numerical column to a categorical column. So this is the training curve, and we also evaluate the accuracy, and for this task, it achieves 83% accuracy. So what's happening inside? Internally, there are different subnetworks that handles different data types. That is the text net, which is based on the pre-trained model, the categorical net, which is some embedding plus MLP, and the numerical net. And these networks will extract features separately, and these features are combined via an aggregation network.